1 minute. I will also turn
Actually, yeah, he said this is on mute.
okay, good.
Yeah.
Also turn these on, just in case.
Oh, just in case, yeah. That's fine. Thanks.
More power.
My power, yes. I can save my voice for the.
Okay. Welcome all to the morning session of the conference. The first talk of today is by Mauricio Romo. The title is Development or Relation Between GLSMS and Equivalence of Categories. Please.
Thank you very much. So thanks a lot to the organizers for inviting me to this very, very nice conference. It's a big honor. And always very nice to be back in ICTP. So my talk today, as the title said, is about this relation between gauge linear sigma models and equivalence of categories. So it's a collection of old and new results. Most of the new results are based on this paper, this preprint we put out with my student, Pan Lin. And there is a lot of also unpublished results with subsets of these people. Most of them are proper subsets. So let me start to give you an outline. So the outline is the following. So first, I will review some old stuff about gauge linear sigma models and B-brains, and also about the B-brain central charge. So this is some old results. And then B examples, I will present for you something that I term window categories. So this will be given B examples to make it more dynamical. And then some results about monodromy. So most of the new results are contained in these two, and if time allows, I will tell you some new directions based on more speculative work and puzzles. There's always puzzles. So let me start with this quick review of GLSM. So maybe I will keep here on the blackboard a few things so you remember the notation. So for the GLSMs, as you can see there, there are some two-dimensional supersymmetric gauge theories where the target space is a linear space, then hence GLSM. They were proposed by Ed Witten in 1993. And I will characterize this for this talk, I will characterize by this four tuple of elements. One is the gauge group, which is, you can see there the characteristics of the gauge group, just compactly grouped. Also a representation of the gauge group, which will be where the chiral fields live, so it's GLV, so V denotes the vector space where my chiral fields live, and also the superpotential, which is some gauge invariant function on V, or on the dual of B if you are more formal. And finally, there is this set of weights R, which are the weights on the vector R symmetry, which they are not going to appear very much on this talk, so that I went quickly through them. Only remember, I asked the potential to satisfy this condition, so the vector R symmetry is unbroken. On all this talk, it's always unbroken. And the axial symmetry will be unbroken for most of the talk, I guess. So I just wanted to point out that there is many coupling constant, but I will concentrate on this set of coupling constant for these GLSMs that by now, if you are not familiar with them, they are, I will denote it like this, is usually you denote the real part has theta, the imaginary part has theta, and I will call the space of this coupling constant MK, which is called by the stringy color space, or stringy color moduli space. This constant by now, if you are not familiar with this, just know that they are labeled by the Lie algebra of the gauge group. Okay, that's a little bit of an approximation, but for this talk it will be enough. So yeah, that's what I want to keep there. So then I had to say a few things about B-branes. So I said something about GLSM, so how to characterize this gauge theory. Now about B-branes. So B-branes are boundary conditions and boundary action for these models that preserves half of the supersymmetry, or one half of the supersymmetry. There's, of course, if there is B, there is A, but we are not going to talk about A. We're going to talk only about B. So I will tell you that these boundary conditions, boundary actions, you have to impose for chirals, and also because it's a GLSM, also for twisted chirals. So the part for the chirals is what I call here algebraic data. So in a nutshell, I'm not going to go into all the details, but in a nutshell, this algebraic data that characterize this boundary condition is this triplet, okay? With something I call T, rho M, and rho and Rm. So this T is a matrix factorization of the superpotential. So what that means? That means exactly what is there. It's an endomorphism on some space M, which is a CMB free module, such that this squares 2W times the identity in M. So in other words, it's like, you can think of it as just a matrix with entries, polynomials on the chirals, and when you square, it satisfies this condition. But because everything is gauge variant, I mean, you have a gauge group, you need to also specify some action of the gauge group in this space M, and also specify a set of weights that characterize how the vector R symmetry act on this space. And it has to be compatible with these two. And the compatibility is this equation here. No? So that this should be not, so just the most thing to remember is this matrix factorization. Okay. So next. So, okay, this is a lot of information, but you don't have to read it all. This is what's the boundary condition for the twisted chirals. So the boundary condition for the twisted chirals, by now, it's something that looks like an A-brane, but by now we are going to say that the boundary condition is given by specifying some contour or some middle dimensional subvariety, LT, because it can depend on the value of that T, inside this Lie algebra, complexified Lie algebra of the torus, of the Cartan. I will give you later a better characterization of this abstract, or maybe for some of you mysterious conditions of the L. So by now, just think that this is just a middle dimension. This is specify the condition, the boundary condition for the twisted chirals coming from the vector multiplet. So just to keep track, these these are going to become the most important players, which is part of the B-brane. They form a category that has been studied by mathematicians like Katsarkov, Ballard, Favero, and also physicists like Herbst, Horry, and Page. So this is a category of matrix factorization of W, which is equivalent with respect to the gauge group. So I'm going to denote this is a category. I didn't specify for you the morphism, but you have to believe me it's a category. So we are going to write it like this, MF, GW. Yeah. So now I come to the third object. So all this review of relatively old stuff. at least 10-year stuff, which is the central charge of the V-brane. So I told you the V-brane on the GLSM is specified by these two guys. So the central charge is a function that is a function of B and also is a function of LT. And there I specify that what the result is that you get a function that's holomorphic in these parameters T, in this color moduli or colors, stringy color space. And and it depends only on those parameters. They are in this very simple way, in this set classical here, like this exponential. And it's an integral. It takes the form of Amelin-Barnes integrals, like the ones that Otto presented yesterday. And it looks like this, with this. So it's a gamma function. So it's very elementary. You don't need to also learn all this detail. What you need to know is it depends continuously on T. And it depends on the B, on this boundary condition, via this character. So it doesn't depend on the specific parameters of T, but rather on this rho m, on this weight. So this is the central charge, it's a function. So now I can say for you, all these other abstract conditions on LT, I can summarize them like here. So this contour, LT, is a Mill-dimensional continuous deformation of this real contour such that this function is absolutely convergent. That is exactly equivalent to all this blah blah that was on the other slides. So this function makes a connection between categorical stuff and kind of more analytic stuff. So this we're going to play a big role. So let's see. Now, before moving to the window categories, let me give you a collection of facts that are going to be handy if you are not familiar with them. So fact one, I already said it. Fact one, yeah. Fact two, unsurprisingly, maybe for some of you, if the gauge linear sigma model is not anomalous, meaning the rho m, this rho m factors through SLV, this function satisfies some differential equation, sometimes called Picard-Fuchs equation, that only have regular singularities. Only regular singularities. So it has there's some monodromy there. That's the monodromy of the title that's coming later. But that gives you the connection between these two things, the category and this analytic function. And some facts about this category that so far is like something just some artifact or something defined on this gauge theory is, if you are familiar with this GLSM, so let me say it like this. You know that the infrared theory, for example, we are thinking on the non-anomalous case, okay? So non-anomalous meaning non-anomalous axial symmetry, or sometimes called Calabi-Yau. You can compute the classical, what we call the classical Higgs branch, which is this, which for physicists is this YZ. This is a moment map associated to rho m, to that rho m. So this symplectic quotient is just what we call the D terms, usually. And we also have this potential. So given this, we can define the B-branes on the infrared, like on the infrared theory. If it's non-anomalous, it's a CFT. So the category of B-branes on the infrared is something I call abstractly like this. You can think of this, I'm not going to go in details, but something called coherence matrix factorization. So it's like matrix factorizations of W inside now this curved space. More, maybe more natural to you is in the case where these intersections, so the critical points of W intersect with YZ, is some smooth, if this thing is some smooth projective variety, for example, this becomes the derived category of coherent sheaves on XZ. So this is a case where I hope some of you at least are very familiar. So first question, since that's a very algebraic thing, you may ask if that thing is equivalent to this one. So the answer is, of course, no. It's not equivalent. However, one thing that is also now proven mathematically is that there exist infinite embeddings of this category inside this one. So these embeddings, these WS, which are subcategories of this thing, here is WS, are what is going to become the window categories. And they are labeled by some abstract label S here, but the idea is now next to demystify them. So this existence of this embedding is, as I say, is a theorem studied by Halper-Leisner and also by Ballard, Katsakov, and Favero. And in the physics, it was originally proposed by Herbst, Horry, and Page, studied in abelian gauge linear sigma models. So let's go to next. So now it's time to demystify this. Time to demystify this, and this I promise I will do it with an example, okay? So because there are some conditions on B and L, of course you can ask if these conditions are in tension somehow. Like, how do I know if these good conditions for L are okay for every B or no? And indeed, that's a subtle question, and that's an important question. So that's what we are going to answer with examples. So consider this GLSM, which is a U1 GLSM for a Calabi-Yau hypersurface in projective space. So very simple. That's the partition function there, yeah, very up. And this is the question. So this is the question you can ask. So here, first, this diagram is covering of the MK. In this case, there's only one T. And these crosses here, there is some crosses, there are some crosses. The crosses are the singularities. These are some singular points because, as we know from the old times, the GLSM, this space is not, there are some points at T where, there are some points at T space where the model becomes ill-defined. There's some non-compact Coulomb branch, for example, unbounded Coulomb branch. So these are singularities that here are marked like this, and that's a specific location. So you can ask, okay, now if I have that function, I have that B comma L, and I wrote for you some path here, which you can consider it as some compact, some specific theta, this path P. You can ask, okay, along this path, do I always have a contour LT that's compatible with whatever B I put there? So the answer to the question is yes, sometimes. Yes, sometimes. So the only situation when there will be a path LT compatible with B through all these paths is if this B, so if the weights of this representation belong to some interval like there, this interval, which is an interval that depends in which theta I'm located. More precisely, depends on this floor, or theta over 2 pi. So there's a condition on the weight. So then because of this, it clearly looks like a window. Then you call this window, so W, and depend on K. So it's a subcategory of this thing. And now I can answer the question of before, and this, for each K, there exist functors implementing equivalence between dv cog of X, is the Calabi-Yau hypersurface, and also there is another implementing the equivalence with the category of matrix factorizations on the Landau-Ginzburg phase. But all this talk will be focused on this, on the geometric phases, as we call.
Could you remind us?
Yeah.
The little QA are the R symmetry weights, is that right?
Oh,
what
no,
are the little QAs?
These are the weights of this. Part of the data of the B brane, of the boundary condition.
Yeah, indeed. But what was the zeta sub M?
Where is?
In your matrix factorization. I'm just trying to remember what they were. The QAs, the little QAs.
Yeah, little QAs only appear here. Only appear there. These little QAs are part of the data of B. Is the weights of, so B, you need to specify the matrix factorization, and also the some representation acting.
The module M was a representation of G in the R symmetry. I'm just trying to remember which one it.
This is gauge symmetry. This is R symmetry.
Thank you.
Yeah, no, yeah, that's why it's R. And the other is rho because very good. Yeah, thanks for the question. Yes. Okay, so this is what happened. This case is very old. This was solved by Kentaro, Hori, Herbst, and Page, 2008, along with many other abelian cases. But let me show you some slightly new things. So here you don't have to read this fully. So here I'm going to give you another example if now you go to a non-abelian model. So this example is a model where, maybe I can use this part of the blackboard. So this is a U2 model. It's the gauge group U2, and you have a Kähler moduli that has two large volume points in this case. One is a sigma model on a Calabi-Yau threefold, which is a complete intersection of 7 planes in G27. And the other is this so-called Pfaffian Calabi-Yau that lives inside P6, that is given by the Pfaffian of some matrix. They are both algebraic varieties. They are not birationally equivalent. And this is the model for it. And here is the partition function, this set in case you are very bored and you want to do some computations. But that's not the idea of this slide. This is just to mention also that this indeed is satisfy this differential equation, this very nice differential equation, where theta is something is z ddz. I didn't put it, but you can check that this thing has only regular singularities, and indeed the singularities that you can also compute using the effective twisted potential on this model are 3. So you have like 3 points here that are singular. The whole 5 points are here. Very good. So what's up with this guy? So you play the same game. You can ask the same question, but there's some difference, some variation of the problem, because now the Kähler moduli looks like this. It looks. This is again covering of the Kähler moduli. I just decompactify theta. So here again crosses. I have 3 crosses corresponding to the singular points and copies everywhere. So now I can ask the same question. I can take a path here, for example, like this path called 1 and this path called 2, and I said, okay, well, can I find some when I can find a contour LT that's admissible or that is nice through all these paths that make the function converge? And the answer is, again, some restriction on the weights of this representation of the gauge group. But now,
what is the relation, I got lost, what is the relation between this place where L lives and the place on which W is defined?
The place where L is and the place where W is defined. Yeah.
Are they the same or different?
Different. Yeah. This L lives on some, on this here. This L lives on the complexified maximal torus, if you want, of the gauge group. It's something related to the gauge group. The W, yeah, I didn't put it. W is a function on this space B, which is a space where the gauge group acts, but it has nothing to do with this T. So this is like, yeah, and it's G invariant.
And the thing you integrate on L, it has to do with W or not?
No, very good question, yeah. Now at this point, W is only to specify this matrix factorization, but when I write this function, like this one, for example, you see here is an example. So this integral is over the torus, over the complexified torus of the gauge group. It's like an integral over the gauge group. Here there is no W. The space of W is, or the details of W are no longer present here.
Okay, so where did that function come from?
Which function?
The one you're integrating.
This whole thing?
Yeah.
That's a supersymmetric localization. So that's the partition function of a model which is like a disk, and you have B brane at the boundary, and you have here near the tip, you have something like an A twist. So it's some partition function construct.
My question is just, did you use W in order to produce this formula that you're integrating or not?
Use it to produce the boundary condition, because the boundary condition is a matrix factorization of W. But the details of this boundary condition that enter on the formula, it's not, has nothing to do with the coefficient of t. It's part of the data of B, but not the whole details. This is a discrete dependence on W, if you want, because it only depends, yeah, exactly, on the weights of this representation. So let's say you have W is like x squared, something like, or x times y. So I can write t that's like this, for example, right? That squares to x times y. So this could be like W. Then because I have a gauge group acting on x and y, I have many choices for how the gauge group can act compatibly on this matrix.
I'm not asking about T, I'm asking about the thing under the...
Oh, L. This? Oh, all this thing.
Yeah, the thing which you were integrating, where did that come from?
Oh, it's a one-loop determinant. It's a one-loop determinant of the gauge theory. It's part of the gauge theory. But no, yeah. Okay, maybe I can clarify it. I can clarify it later. But in a nutshell, all the integrand has only a discrete dependence on B. So there's no W. The coefficients of W are nowhere here in this integrand. It's a different space. Okay. Okay, where was I? Oh, yeah, I just said, so you can play the same game here and ask for this path if you have some kind of a window, meaning there is a restriction on some subcategory of this MF, so some condition on the weights of this B, such that you can find it convergent, this LT that make the function convergent. And yeah, as I said, the answer is yes. But here there's a lot more complications. So first of all, you have to deal with representations of U2. So I put here, I give you an example of two window categories, and I just describe it like this as a subset of representations of U2 that are compatible with the existence of a path, of a contour LT through this path. So in this case, one of the main complications, this is part of unpublished work with Knapp, Hori, and Eger, is that here you have some other paths that you can also have paths that are like this. So
Right,
maybe
Mauricio, could you back up a second? So the window categories, you have two window categories, and those are the representations. Those are simple objects or something in the window category. They generate the category. Is that the idea?
right, these are the generators of the subcategory.
Okay, good.
Yes. That's right. Yeah, sorry, I didn't call it W here, but they are W. But the point is here you have, because it's more complicated, fundamental group of these 5 puncture sphere, you can have other paths. So you can have paths like this. So you may naively think that this path, the window category, is something like some intersection or some union of these two, but it cannot be. It has to be something kind of in between. So that's really hard to determine. I mean, that's the reason why this thing is unpublished. From consistency conditions, you can actually determine yet another subcategory associated to this curved, what I would call a curved path. The other are kind of straight path. Well, so that's this part of work in progress. Okay, this is just a rough drawing. You can now put all these things together, and by looking at, because all these W should be equivalent. So I'm not going to describe this psi and phi now because there's no time. But you can see from there that given a singularity, I can kind of go in a loop, and then the composition, like this psi plus composed with this psi and psi minus, is some object and the group of autoequivalence of WK, which at the same time is related to autoequivalence of some infrared category that I can study, that it can have a more geometric meaning if you want. So if you have the knowledge, this is just to say that if you have the knowledge of this window, you can compute these monodromies at the level of the autoequivalence, or if you want, you can evaluate this function, and you also have the monodromies at the level of the partition functions like the ones that Albrecht was talking about. So here's an old example about the hypersurface. If you play that game on the hypersurface case and you go through these loops, here is always in my mind the quintic, so that's why it's 5, but you can replace it by n. The most interesting is that you have this, again, these are all results, that you have this loop here. You can determine that this loop here around this so-called conical point is this spherical functor with this spherical twist with respect to the structure shift of the Calabi-Yau hypersurface. Okay, but that's all result. More interesting, you can play the same game on this non-abelian or 1. And you can get some interesting, here you can compute these other monodromies that you don't have a priori way to think, to predict what they are going to be. And they happen to be this actually this very simple twist, this very simple spherical twist by OX, as X is the tautological bundle, rank 2 of a Grassmannian pulled back to the X, and here is some symmetric product of it, twisted by 1. So, no, not yet. So this is something that was predicted in this unpublished work, or maybe published in some very obscure places, but also some mathematician, Will Donovan, studied this problem very recently, and he also showed that it's compatible with his way of understanding the same problem. Let's see, what's next? 2 parameters, yeah. So now it comes the more new stuff as well. All this unpublished, but not so new maybe. So finally, for this set of examples, I wanted to talk about a 2-parameter non-abelian model. So you may think, okay, this was an abelian model. Going to a 2-parameter is just going to, no parameter, non-abelian, it's going just to complicate your life, and just you are going to tell me I'm very strong, I can do it in that case. But no, that's not the main point. I just wanted to convey that actually there's new phenomena here, like there is this more singularities appearing. There is also new phenomena on the, if you go to higher parameter case. It's not just, it's technically more complicated sometimes, but that's not the whole point. So I will give you one example that's on that paper with my student. You don't need to read all these details, but this is GLSMs that are associated, that we studied with Jokers, Kumar, Lapan, and Morrison, like also kind of 10 years ago. These are models that had a geometric phase, where the geometric phase is a resolution, classical resolution, of what's something called a determinantal variety. So determinantal variety is something like this. You take a section, you take 2 bundles over some, let's say, smooth projective space B, these 2 bundles F and G, and then you take a section of the home EF, and you ask this rank to be less or equal than K. So it's a very singular variety in general, but you can resolve it classically, and there is a GLSM for it. So instead of boring you with the details of this classical algebraic geometry now, I will just give you one example and show you on that example what I claim is a kind of new phenomena. Okay, 20 hours left only. Yeah, very good. So here, this is the GLSM, the G, rho, etc. content if you are interested, but the only thing I want to point out on this slide is this an example, which is a very simple resolution of one of those varieties. And the only thing you have to remember is that this is some Calabi-Yau threefold. It has 3 phases, but just focus on this phase XA, which is some Calabi-Yau threefold that lives on G to 4 times P7. Okay, it's smooth, it's very well behaved, and it has now the projection. I cannot write MK, but the projection of MK to the R2 looks like this. So these gray lines are kind of the classical boundaries of these chambers on MK. So, however, in the same case has in this, like in this example or in the quintic, to determine these singular points here is kind of a highly quantum effect. It's not something you are going to determine classically from looking, when I say classically, I mean just looking at D term and F term equations. It's something you need to work more to determine it. And here is no exception. And instead of having points, here you have some divisors that I call delta 1 and delta 2 that asymptotes to these gray lines. But in general, you see, they are very complicated. They are order 4 and order 8, these two. So here I focus on this point There's a large volume point there where there is XA. So we're going to focus on that point for this example. So one thing you can do is, and let me write it here, maybe. So one thing you can do is that you can take base point here near XA and try to compute these two path 1, let's say, and path 2. And you can ask again the question if there are some window categories when crossing these boundaries. And there are, and if you believe me, these are not so hard to compute. But this is not the main issue. This is an example where they are particularly simple to compute. And you can see if you cross on one direction, if you can go in this direction, it imposes some conditions on the weight under the representations on the weights under, I don't know where I put it. I didn't put it, yeah. So the gauge group here, in this case, the gauge group was U1 cross U2. So in one case, it imposed a condition on the weights of U2. In the other crossing, it imposed a condition of the weights of U1, of the U1. Here, if you cross like this, it imposes a condition on the weights of the U1. If you cross like this, impose these conditions on the weight of the U2. Okay, very good, but that's very analogous at the story before. And if you compute the monodrome is associated to those windows following the same procedure as before, you can also find some nice expression for one of them for this Tx, which will be like taking a loop like this. And if you take a loop like this, you get another that I call Ty, which is more complicated, but more complicated in the sense that I don't have an immediate way to write it in terms of elementary twist or spherical functors. So how can I write, but I'm going to claim now that indeed the fact that we have this quantum effect, these divisors here, delta 1 and delta 2, will teach us how to write this Ty in a simple way. So what you do is an idea that was on abelian models long ago on some papers by Aspinwall, which is you just look around here. You want to make here, we are going to make this crossing. You look around here, you put a trisphere. So if you put a trisphere, center at this intersection, which all of them intersect at one point, intersect very, very non-transversely. You look at the sphere there, and you take the intersection with the divisors. And this thing happened to be a link. And so then around there, the moduli space look like a trisphere with a very small radius epsilon with this link removed. So I will show you the link because it doesn't look that bad. So the link looks like this. And it's a very nice, it's something that I learned is called a nested link. So you have one component coming from delta 2, one component coming from delta 1, and this red coming from the divisor at infinity, w equal to 0. So crossing, doing the loop around that, this Ty corresponds to going along this red line, actually. Along, it's something that goes very parallel to that. So the only thing that you have to do is to brush up your kind of elementary school computations of fundamental group of these link complements and decompose the loop along this red into little loops that are around, now they are surrounding this, each of these components. So actually this thing is generated by loops around the red, black, and blue. And you just have to associate to each of these loops one of these autoequivalences. So the answer, it turns out to be this assignment. The kind of complicated thing here is to guess this assignment. There is no kind of algorithmic way to do it that I'm aware, but it satisfies many consistency conditions. Then after you do that, you can decompose.
Sorry,
this.
Marita, could you remind us what is, or remind me, what is the, what are these functors, T sub S and T sub O? You said, these are functors on these window categories, which are subcategories of the category of representations, right?
Yeah, so
of the
in this case, the window category here, there is going to be like the right category of XA.
Okay.
So this, yeah, sorry, maybe I didn't say. So this T of S, T of OX, these are all autoequivalents of this category. So they are spherical twists with respect to these objects.
What is a spherical twist?
Yeah. So spherical twist is like, let me write the formula. So it's something. So if you have here an object E, I will just write. So the spherical twist TE, E is the object under the. It's like this. It's like many cones. I think this is a minus I.
Okay, thank you.
Okay, I knew they were going to ask me that, so that's why I wrote the formula. Yeah, it's like taking many cones with respect to this object and its shift. That's one very informal way to say it. But if you do that, you can now this Y that I say is mysterious. Maybe it doesn't look that short to you, but indeed it decomposes into simpler functors. Thanks to the nature, actually, you have to really use that there is this quantum. You really have to think about this kind of quantum effect here, meaning this that this gray is kind of the classical wall, if you want to call it like that. But no, you have to think in terms of these divisors delta on this discriminant. Okay, so you may ask, okay, now I have to say some puzzles maybe. You may ask what happened if you try to do the same thing, but in the other crossing, in this crossing. Well, you also can write a link there. However, this link doesn't look that happy. It's a very complicated link, but it's not, I mean, the complication is not that because it has tons of crossings. That's not the main complication. I mean, if you have a student, you can solve that. But the thing is, but the problem is here, if you see this closely, is that there are more than 3 components. And 2 components comes from the same divisor somehow. It's like this. So guessing what's the functor of the autoequivalence like this to associate to this and to this is, we have some proposals, but it's too much of a guesswork. So in this case, I will say we don't have concrete proposals how to assign these functors to each component. But the happy part is that as I promised, I didn't show it here, but this kind of effect generalized to a big family of Calabi-Yaus that can be modeled with this type of GLSM, not necessarily in G24 cross P7. It can be a more complicated space there. As long as the singularities of the determinantal variety that it resolves are nodal points, this seems to be the case, at least in, as I say, it's many examples. There is no theorem here. So that's it. That's that. This is what I wanted to say. This is kind of the more speculative part. So now, so far we have all worked with this Calabi-Yau. So maybe we're going just to mention some work in progress, but still is very much in progress. Just you can ask what happened if there is no, if you relax the condition that the axial symmetry is unbroken. So you consider, for example, GLSMs that has geometric phase that are sigma models on Fano varieties. So you don't have to look at all the details on this. Let me just mention, because it's a bit long to explain something. Here is an example of a GLSM with target space just Pn. In this case, there are many things that are different. There is some RG flow, some RG flow that acts, so there is some RG flow effect on the color, on these color parameters we were talking about before. And also you can have some non-trivial Coulomb branches rising up in some regions of your space. So what happened in this case is that you have to interpret it differently. So one thing is that the rising of this Coulomb branch signals the existence of semi-orthogonal decompositions on the derived category of this Fano. In this case here, I wrote the simplest example, which is Pn. The existence of Coulomb aqua signals the existence of this very well-known semi-orthogonal decomposition of Pn. So there's also a way to define windows here. I'm not going to go into the details of this. I'm just going to mention, I wanted to mention this because this seems to give, there seems to be an interpretation using this framework, if you relax the Calabi-Yau condition, of the so-called Dubrovin's conjecture, which is some conjecture about the Stokes matrices, which will be in this case the Stokes matrices of the central charge, because now the differential equation has irregular singularities. So there seems to be a way to interpret those Stokes matrices using these windows, which you can also define for non-Calabi-Yau cases. And I just want to mention also, because Dubrovin was one of very famous, very distinguished professors here at CISA, and many other people I know work on this conjecture, like some from here, some that studied under him, like Giordano Cotti, Gussetti, and some others. So it seems this gives a nice interpretation of these Stokes matrices. But this is, as I say, is work in progress. I wanted to mention has some future work. And maybe to finish, I will give you some puzzles and speculations as well. So there are some puzzles I wanted to mention of this story. This is the last, this is the last slide, so don't worry. Well, almost the last. So the one is one question, kind of these are general questions, is in the case of abelian GLSMs, there is a systematic way to derive all this stuff, but all these window categories, sorry. But in the non-abelian case, it's kind of case by case. There is no systematic way. So the question is there a relation or a way to systematize the derivation of these window categories for non-abelian? A huge question is what's the mirror of this story? Because there should be a mirror because there is a B, so there has to be an A somewhere, and there is an A on the mirror. But for example, cases like this XA, this resolution here, these are very funny examples because they have no known geometric mirror. So everything is just done on this side of if you want, of this side of the mirror, but the other side is completely unknown. So that will be interesting to understand. And of course, there's these two things that I was just talking. This is okay. You can include on all this story, consider case where there are isometries or flavor symmetries, and you can turn on twisted masses on the Z and on the category. This, as far as I know, this has been largely unexplored actually in this context. And finally, as I mentioned, you can try to find a new explanation or alternative explanation to this Dubrovin conjecture has maybe some kind of generalization to non-geometric case, for example. Grazie mille. Grazie. There is one there. Yeah, okay.
Nice talk. So as far as the mirror symmetry, it does work for generally for all of these. You just take the, for example, for the non-abelian ones, the same method you do for abelian ones that we did with Kentaro works for non-abelian ones. You just change the measure. So in other words, you go from, for example, for the UN, you write it like in terms of U1s.
Oh, so there is a mirror story that. That would be nice actually. Yeah, to implement this.
Thanks for the talk. I had a question. I mean,
Yeah.
if you have this, in the two-parameter model, you had this tangency, right? This
Yeah.
place.
This tangent.
And then you took somehow like the Breeze-Con sphere, you get these complicated links.
Yeah.
But on the other end, Hironaka says you can always resolve that to make it normal crossing. So I
That's
don't
correct.
understand the relation.
The short answer is I don't know. I tried to do that, but that was looked very complicated.
So that is for this analysis simply more complicated, but would it change really this window category, how you treat the model?
Hopefully doing that, you are going to, right, you are going to resolve here, right?
Yes.
So you are going to get many exceptional devices, some mess.
Until it's
so I will hope that then the monodromy can be expressed as kind of loops around all these different exceptional devices. It should hopefully should reproduce something like this. Yeah, but nobody have done that.
You.
Thank you for your talk. I think a ALT is defined only up to orientation, right?
Up to?
Orientation. For example, consider
The LT, yeah.
Yeah. Also, for the final case, you mean the Coulomb branch? You mean you also need the data about a soliton for matching the category.
Yeah. So the case of when there is a Coulomb branch, like when it's anomalous, is more complicated to define the category at the Coulomb branch. I mean, the knowledge of the existence of the vacuum just tells you there is this decomposition. But of course there is more, right? You have to work the morphisms. That's yeah.
Can you go back to the page I was asking questions about?
Very good. Yeah. Oh.
So
Well, there's a function. I mean, it's the same function.
yeah, that's okay. That's okay.
Yeah.
So if you so here you have some space T, you have some function on it. This function you're integrating, and you've drawn some Lagrangians in that space. And if someone had done that and showed it to me and asked, what is this? I would have thought the category of those Lagrangians with respect to that potential would play some role. And so my question for you is, what role does that category play?
The L. The category of the L's.
The category of the L's, the Fukai category of the L's with respect to the potential that you're integrating.
Yeah, so the thing is, maybe this is the thing that confused you. So there are two potentials on the story. One is this potential that
I'm not asking about that one now. I'm asking now about the one that you're integrating.
You can take, so you can take this integrand and look at the asymptotics of this integrand. So the asymptotics, it will be a function of this sigma. So the asymptotics, it will look like exponential of something, and that something will look like this. That's the potential. That's the potential you are thinking of.
Yeah, sure. So the question I'm asking you is, having written that and having drawn these Lagrangians in that T, you might be tempted to say, I now consider Fukai category of those Lagrangians in this space with this potential.
That's good. Yeah.
And the question I'm trying to ask you is, does that category play a role in your story?
So in my story, that category plays kind of. So short answer is no. That category plays kind of a very like an auxiliary role. Like if I have this function and I only think of these Lagrangians that make this absolutely convergent, for example, if I'm like around here, for example, around at a point here, Actually, there is no condition. For every V, I will be able to find a Lagrangian that satisfies the conditions of making this convergence. So in that sense, I will kind of, if I'm very close to large zeta, for example, I will completely ignore the else. I will kind of drop them from the category. I will only work with B. However, if I look at this path, the interaction between this L and B gives me this condition. But at that point, I completely forgot. I mean, I don't use the category generated by the else. That's the short answer. I don't use it for anything, so in this picture.
So I think if I use the integral representation of gamma function, so introduce an extra variable for each gamma, and then integrate out sigmas, then this integral will be a counter-integral in a higher dimensional space, which will represent the mirror that Kumran was talking about. So
Indeed, if you write the integral representation, you get the potential Kumran was talking about. The difficulty is to make this kind of analysis. Now using that perspective. Now you have to change B by A. And
if there are no more questions, let's thank the speaker again.
This, okay. You don't have to point, you can point whenever.
Yeah, good.
And don't keep this pressed, otherwise it goes off.
Okay, yeah.
Okay, the next speaker is Lawrence Eberhardt, who is going to talk about a landscape of 2D string theories.
Okay, thank you very much. Let me join the other speakers to thank the organizers for organizing this wonderful conference in a very wonderful place. So thank you very much. And today I'll talk about work in collaboration with fantastic collaborators, Scott Collier, Beatrix Mühlmann, and Victor Rodriguez. We put out one paper last year, and the second part of the talk is work in progress. Okay. So let me start. So we all know that the landscape of string vacuum is extremely complicated, but there's one place where it's much simpler, namely if you just consider bosonic string theory with a 2D target space. What I mean by 2D target space for the purpose of this talk is basically any string theory bosonic string theory that does not have a tachyon. We'll see examples. And that one is much more controlled, and essentially there are two examples in the literature. One is the so-called PQ minimal string. I'll explain what that means. And it's well known that it's dual to a double-scaled two-matrix model. And there's another example, which is the seek-to-one string, which is a free boson coupled to Liouville theory on a world sheet, which is dual to matrix quantum mechanics. So that's a very restricted set of examples. So there's a question, is that all? And can we show that it's all? Can we classify that landscape? And so on. Okay, so today I'll just focus on these types of models, namely the minimal string. I will not talk about the seek-to-one string. So the persistent paradigm here is that if we construct some string worldsheet theory that is consistent of a matter theory, and we complement it with a Liouville theory such that the total center charge is 26, and couple it to the usual BC ghosts that we have in string theory to make the path integral well-defined. Then we can integrate over the moduli space, and we get some string theory. And because we just took basically these two very simple ingredients of a matter CFT, we'll see what kind of matter CFTs we can take. And the Liouville theory, we get very simple sort of holographic descriptions, if you want. And the types of theories that appear as the space-time theories or the holographic duals can be written as double-scaled two-matrix integrals. So these are just these types of matrix integrals where you have two matrices that you integrate over with sum of two potentials, and they are coupled in a simple way. Sometimes even one matrix model is enough. Okay. So one way to plot the kind of theories that exist in this, of this kind is to plot them in the space of center charges of the matter theory. So your matter theory can have any center charge that you want, and then you put the corresponding Liouville theory whose center charge is 26 minus that center charge to make up the string theory. Basically, these PQ minimal models, so the PQ minimal string is located, represented by these red crosses. So the center charge of the matter theory, it's a Verzoro minimal model, and takes values less than 1, and there's basically a dense set it can take. So there's some rationality condition on the central charge. But today I'll discuss that this is not all, and there's at least two more constructions you can do that are quite interesting, I think. And basically, the first construction I'll tell you about covers this whole this whole interval from -infinity to 1. So now it's not just a dense set, it's the whole real line. And then there's a second construction, which is a bit more funny, where the center charge is actually complex. And you make a matter theory of complex center charge. So I don't know whether that's everything you can do, but that's at least two more entries in this kind of landscape of minimal string theories. So let me explain these theories. So let's start with the simplest one. And I'll not take, so the simplest case is when you don't take the P, Q minimal string, but just the 2, P minimal string. In general, in the P, Q minimal string, P and Q need to be co-prime. So 2, P is the simplest thing, essentially. And in this case, the matter theory just consists of this Verzoro minimum model. And Verzoro minimum models are specified by 2 co-prime integers. And then, as before, we couple it to Liouville theory and to ghosts to make up some string theory. And so it has been known since the 90s that there's a dual matrix model description. And basically, it's a double-scaled matrix model again. Now, a single matrix is sufficient. And to specify the matrix model, basically, we just have to specify the density of states at leading order in large N. And the density of states takes this form. So it's like a slightly complicated looking function, but it's polynomial, actually. You can use, well, yeah. Okay, so that covers some part of the negative real axis, or real axis less than 1. And, but now it's not dense, so it's some series of theories. And one thing that has been discussed recently in the literature is that if you take a limit where you take this P to infinity, things actually simplify. So now you go off to -infinity in the center charge, and the theory reduces to a theory that is called JT gravity in the literature. It's a theory that we'll encounter later. It's basically a theory that just computes the Weil-Petersen volumes of surfaces. Okay. We can move on to the P, Q minimal string, where P and Q are now general, but still co-prime integers. So it's exactly the same on the worldsheet, except that I replaced this with the PQ minimal model. And it still enjoys a matrix model dual, but now we need to have a double-scaled 2-matrix model. And to specify the 2-matrix model, the most convenient way to do so, essentially, is to specify the so-called spectral curve. So the spectral curve is some Riemann surface, and all the perturbative quantities so that you derive in the 1/n expansion of the matrix model are take value or naturally live on this Riemann surface. So in this case, it takes the simple form where x of z is a Chebyshev polynomial of z, and y of z is a Chebyshev polynomial also of z of degrees p and q. And z is just some rational parameterization of that curve. Okay. So now let's move on to the new models. So one thing that we looked at is that there are more matter theories than just these minimum models that you can take. And one is known as time-like Liouville theory in the literature. So you can couple Liouville theory to time-like Liouville theory. Time-like Liouville theory is a theory that exists for any center charge less than 1. So any real center charge that you want. And again, you put your ghosts to define a string theory. And you can ask, so this is a tachyon-free bosonic string theory. So you can ask, is there also a dual matrix model? And will turn out yes. The answer is yes. And there's actually a one matrix model dual. So one matrix is enough. But now the density of states takes this form. So it's a more complicated function. It's no longer polynomial. And it grows exponentially fast if you go to high energies. And we'll encounter these string amplitudes later on in this theory. And they will turn out to be deformations of Weil-Petersen volumes. Okay. And so the last thing I'll discuss later on is this other theory that we very tentatively call Liouville squared string theory, but we're very open to better suggestions for this name. And so basically this is now I couple two Liouville theories to each other. So both are ordinary Liouville theories, but the funny thing is that they have complex center charges. So Liouville theory exists for any center charge where the center charge is actually not in the interval from -infinity to 1. But in particular, I can choose this combination, 13 plus imaginary and 13 minus imaginary, so that the sum is, again, 26. And now you see, you can think of one Liouville theory as being the complex conjugate of the other theory. If you write down the reality conditions, they couple this Liouville theory to this Liouville theory. That's why I'm taking this symmetric combination. So that's, again, a well-defined bosonic string theory without tachyon. So you can compute integrals over moduli space, and you can ask whether there's a dual description of this theory. And the answer turns out, again, yes. It's more complicated than the previous one, involving time-like Liouville theory. But again, there's a two-matrix integral, which is described by this spectral curve. So now this is a bit of a wild spectral curve that we'll discuss later on. It's a curve that has infinitely many singularities, but you can still deal with it. And in particular, all the string amplitudes of this theory will be computed by some topological recursion. Okay, so that's a brief overview of what I'll explain. So both of these theories, you can think of them as being sort of irrational cousins of the PQ minimal string, because both of them exist for continuous values of center charges, and also the string amplitudes, they are continuous functions, because vertex operators in Liouville theories, they depend on the continuous parameter, the Liouville momentum. So everything is kind of nicer because all the amplitudes will have nice analytic structures, and that basically allows us to analyze these theories in much, understand these theories, I would claim, in better ways than the ordinary minimal string. So I think it's a fruitful thing to look at now. Okay. So let me get started. And first I'll talk about this time-like Liouville coupled to space-like Liouville, which we called Vera-zero minimal string. Again, maybe that's not the best name, but okay. So again, recall that we're looking at this worldsheet theory. So it's a Liouville theory, and the matter theory is this time-like Liouville theory coupled to BC ghosts. Okay, so that's a precise definition, but let me remind you what this Liouville theory and time-like Liouville theory are. So let's start with Liouville theory, that is probably more familiar. So Liouville theory is some non-compact conformal field theory. It's a unitary conformal field theory, and it solves the CFT crossing equations. So that was established in a series of works. And the center charge is convenient to parameterize it in this way. So the center charge is 1 plus 6b plus b inverse squared. And so this is just a different parameterization. Usually we don't talk about the center charge, but we talk about this b parameter. And in particular, we can take the b parameter in the interval from 0 to 1. Then the center charge is bounded from below by 25. Because the center charge of the time-like Liouville theory will be bounded from above by 1. And the spectrum of this theory is continuous, and it's bounded from below. So all the primary states in the theory are scalars, and the spectrum is bounded from below by c minus 1 over 24. So in particular, this is bigger than 1, so the vacuum is not part of the spectrum. Okay? The vacuum not being part of the spectrum is the main reason why there's no tachyon in the spectrum of this string theory, because the tachyon comes from the essentially from the vacuum state in the matter theory. Okay, so that's the spectrum, and also the structure constants are completely known. They're given by the famous DOZZ formula. So if you ask what is the 3-point function of 3 vertex operators on the sphere, then they're given by this function CB. It's some explicit function involving some special functions, some Barnes double gamma function. So it's quite a complicated function, but it's very explicit. And essentially by now it has been proven that this forms, in this series of works, that it forms a consistent CFT. So once you have the 3-point functions on the sphere as in any CFT, you can define an n-point function on any genus G surface. So you just decompose this correlation function into conformal blocks, and you need to integrate over all the intermediate states. And for every 3-punctured sphere in this decomposition, you put a DOZZ formula. Okay, so these correlation functions can be defined on any genus G surface. So let's move on to time-like Liouville theory. So again, this is some consistent solution to the crossing equations. Now it's non-unitary because the center charge is less than 1. And also this has been analyzed in a series of works, but I would say it's much less understood than and much less studied than the Liouville case. Should also mention that in the math literature, this theory is known as imaginary Liouville theory. And one thing I should really emphasize is not some kind of analytic continuation of space-like Liouville theory to center charges less than 1. So in fact, space-like Liouville theory does not admit its analytic continuation to center charges less than 1. But still, the parameterization looks very similar. So you, again, parameterize your center charge in a similar way. So this formula you can get from the previous one just by putting this b hat to I times b. Then you turn around the sign, and you turn around this sign. The spectrum looks exactly the same. So it's, again, continuous, and it's, again, bounded from below. And, again, there is a formula for the 3-point function in the sphere, which I call C hat. And the perhaps surprising thing is that it's related to the 3-point function that we saw before, but it's essentially the inverse of the 3-point function of ordinary Liouville theory. So it's the inverse of the 3-point function of ordinary Liouville theory, where you put the momenta to I times the momenta, and you use this b hat for the b parameter of the ordinary Liouville theory. Okay, we'll see in a moment what that means for the string theory. And again, you can define correlation functions by decomposing into conformal blocks. Okay, so these things are reasonably well-defined things, these theories. The Weyl anomaly is, so the center charges have to add up to 26. And if you look at the equations, that means that this b hat is equal to b. And the mass shell condition of physical vertex operators are that the total conformal weight is 1, which means that the Liouville momentum of the time-like Liouville theory is I times the Liouville momentum of space-like Liouville theory. And with this, you can make on-shell vertex operators. Just combine them and put C-ghosts. Okay, and then you can integrate them over moduli space as follows. You just take the product of both theories, you combine with the BC ghosts, which give you the integration measure, and you integrate. Okay, so that's your observables in the theory. And one thing I want to emphasize is that these integrals are actually absolutely convergent. So that's a bit surprising. If you have studied string theory, typically all the integrals over moduli space are divergent and need to be defined by some analytic continuation and so on. But here they're just absolutely convergent. So these are completely well-defined integrals. And so that in particular makes it very nice to study them because they turn out to be very simple. Okay, and for a reason that will become clear in a moment, we call these integrals quantum volumes, and hence also the notation V. Okay, and I just want to emphasize that this is, seems quite a complicated thing, because to define these Liouville correlation functions, you have to know this DOZZ formula, you have to know all the conformal blocks, the Virasoro conformal blocks on some genus G surfaces and so on, and you have to integrate them over moduli space. So it seems like a very complicated thing. But now I want to convince you that these V's are actually extremely simple. And I'm going to do that by showing a sort of, if you're a mathematician, a little bit sketchy argument, which I think can be made more precise. But I hope you forgive me if I'm not super precise. That's why I put the danger sign up there. Okay, so there's an argument how to derive the matrix model. And you can derive it by thinking about Virasoro conformal blocks on your Riemann surface that you consider. And the nice thing that was pointed out very long ago by Hermann Verlinde is that these conformal blocks admit an inner product. And the inner product is as follows. So you can get it by thinking of conformal blocks appear if you quantize Teichmüller space. So if you view Teichmüller space as a phase space and quantize it, then the Hilbert space, well, the wave functions are essentially just Virasoro conformal blocks. And by geometric quantization, you can derive an inner product on these conformal blocks. But independently, you can just accept this inner product. So if you take two conformal blocks, they're labeled, so they live on this Riemann surface sigma, and they're labeled by some Liouville momenta P and P prime. Then the conformal block is just you take one conformal block, the inner product, you take this conformal block complex conjugated times the other one, and you want to integrate over the phase space. And that's what geometric quantization tells you, which is Teichmüller space. So Teichmüller space is the universal covering space of moduli space. But for this integral to be well-defined, essentially the same considerations as in string theory apply. So we need a center charge, because locally this integral looks like an integral that we encounter in string theory. So the total center charge must be 26. And so we need to supply this integral with some other factor that makes the center charge 26. So this conformal block carries a conformal anomaly of C, center charge C. So this factor has to carry conformal anomaly of center charge 26 minus C. And it turns out that the essentially unique thing you can put here is exactly this time-like Liouville correlation function. And then again, you put the BC goes to define the integration measure, and you integrate over moduli space, over Teichmüller space. Okay, so that's an inner product on the space of Liouville conformal blocks. And you can figure out what this inner product is by noticing that it's that crossing transformations with respect to this inner product are unitary. That just follows from the definition. And because they're unitary, that imposes very strong constraints on these conformal blocks. And these constraints allow you to bootstrap a more explicit formula for this inner product. And the explicit formula is very simple. So it just puts all the momenta, the internal momenta, so this bold-faced P is just a collection of all the internal momenta. They're like 3g minus 3 plus n of those. They have to agree on both sides. So with respect to this inner product, the conformal blocks are orthogonal. And then there's some density down here. And the density is basically the OPE density that it appears in Liouville. So for every, so conformal blocks, to define them, you need some pair of pans decomposition on the Riemann surface. And for every pair of pans, you get a factor of the DOZZ formula. And for every cat that you do to define your pair of pans decomposition, you get some normalization factor that you can identify with the inverse of the two-point function in Liouville theory. Okay, so you have this nice formula. And I want to use this formula because this looks actually pretty close to what we want, right? Because this is an integral over Teichmüller space, which is the universal covering space of moduli space, of integrand. Half of the integrand is already correct, because this time-like Liouville theory, and is equal to something very simple. So how can we use this? Well, we can do this slightly formal manipulation and realize that what these quantum volumes V are actually computing, they count the number of conformal blocks that are invariant under the mapping class group. So this number of conformal blocks, formally, you can compute it by saying the size of this space of conformal blocks, which you can write like this, because this rho is just the inverse of the inner product. So I'm just taking the trace of 1 here. And then I divide by the size of the mapping class group. Of course, this is some infinity by infinity, but don't panic. We'll get finite in a moment. And I think one could also improve this argument if you want to, but I'll just continue. And so we can use, for this inner product, we can use the formula, its definition, in terms of an integral over Teichmüller space of the time-like Liouville theory. And here, this integral over P, together with this rho of P, together with the conformal blocks that enter the inner product, exactly build us the correlation function of ordinary Liouville theory. And so finally, we have an integral over Teichmüller space divided by the modulus, by the mapping class group, which by definition gives us the integral over moduli space, because now the integrand is invariant under crossing transformations, And so gauging the mapping class group precisely restricts us back to moduli space. And so that's our definition of V. So V, what V is counting is formally counting the number of conformal blocks that are invariant under crossing transformation, linear combination of conformal blocks. Well, this number of conformal blocks is actually pretty, we can compute it in a different way, namely by using an index theorem. And so it's just because conformal blocks you can think of as holomorphic sections of some line bundle. And because they're invariant under the mapping class group, it means that this is some line bundle over the phase space, which is now just the moduli space of Riemann surfaces. And so you can just apply the usual index theorem, which tells you that this number of conformal blocks, and hence V, should be computed by an integral over the moduli space of surfaces or curves. And then you get this Todd class of the tangent bundle, and you get e to the first Chern class of the corresponding line bundle. And this first Chern class of the line bundle is just determined by the conformal anomaly. So you see the conformal anomaly times the usual kappa 1 and psi are the kappa classes and psi classes are moduli space. And so that captures the conformal anomaly. And this pi squares captures the conformal weights of the vertex operators.
Usually Chern classes are integral classes?
Yes, very good. So you caught me cheating. So the way I cheated is that this line bundle is actually not a line bundle that is totally well-defined on moduli space. It's well-defined on Teichmüller space. But once I restrict it to moduli space, you're asking why this V, I guess, will not be integer.
Yeah.
So this P here, I allow it to be any continuous number. And then this will only be a projective line bundle. It will not be a proper line bundle. So the way I
Projective line bundle is nothing, right? I mean, a line is already one-dimensional. So if I projectivize, I get a point.
Yes, okay.
So, I mean, are you using some kind of L2 index theorem on Teichmüller space?
Perhaps you can do that. Yeah, so as I said, so that's, I put a danger sign, so hopefully you're okay with that. So I started with an integral over Teichmüller space of this integral and divide by modulus by the order of the mapping class group. So on Teichmüller space, this is, as you say, yeah, I need to refine my index theorem because Teichmüller space is non-compact, so I'm not allowed to use it. But once I restrict my integrals back to moduli space, everything becomes well-defined. So perhaps one can make this more precise by using some version of equivariant cohomology where you compute with respect to the equivariancy with respect to mapping class group, but hopefully someone knows more about that than I do. Okay, but if we accept this, so once we are at this step, we have a well-defined integral because now we have an integral over a moduli space of some characteristic classes that we are familiar with. And this Todd class, we can also decode what it is in terms of kappa and psi classes by using Grothendieck-Riemann-Roch on the universal curve. And we can write it as an exponential of well-known kappa and psi classes. Okay, so I admit not everything was extremely kosher. But so once we are at this step, you see that these quantum volumes, they can just be computed by using standard intersection theory on the moduli space of curves. And these kind of integrals are well known to be described by topological recursion. And topological recursion is just a different word for the loop equations of matrix models. So that was established by Einert and Orrington and Einert. Okay, and so you see already that using this description, provided it's correct, we'll make some checks in a moment, we see that these quantum volumes have very surprising properties. So maybe most surprising of all is that there are actually polynomials in the center charge and in the squares of the Liouville momenta of this degree, the degree equal to the moduli space. That was highly not obvious from this worldsheet integral, because in the worldsheet integral we had the DOZZ formula and everything. It was very complicated, but here everything collapses to something very simple. And there's also an unexpected symmetry, and the symmetry maps B to IB, or alternatively center charge to 26 minus center charge, and the Liouville momentum to I times the Liouville momentum. And roughly speaking, that exchanges the two theories in the worldsheet, even though I'm, of course, not allowed to have center charge less than 1 for Liouville theory. Okay, but nonetheless, these quantum volumes, they have this symmetry. Okay, so now we can easily write down some answers. So in the sphere 3-point function, we just get 1. So that one is easy to reproduce from the worldsheet, because I told you for the worldsheet, basically the time-like Liouville 3-point function is the inverse of the space-like Liouville 3-point function. So once you put them together, they cancel, and they give you 1. So okay, that works. And then for the 4-point function and for the 1-point function of the torus, you get these very simple polynomials. And of course, it's easy to make a bigger list. And I just want to emphasize again that it's quite surprising that it's so simple. And also, there is so if you look at the intersection definition of these quantum volumes, it is really true that in the semi-classical limit, which is when the one central charge goes to infinity, the other one to minus infinity, this reduces just to the Weyl-Peterson volumes on moduli space. That's, of course, expected because we quantized the moduli space of Riemann surfaces. So in the semi-classical limit, roughly speaking, every volume of H bar should give us one state. So the dimension of this Hilbert space should be roughly the dimension, the volume of the moduli space. Okay, and just so that you're slightly more convinced that this is true, we checked the 4-point function on the sphere numerically. So we implemented all the DOZZ formulas and the conformal blocks and everything and integrated them over moduli space. And we compared with these simple polynomials, and it seems to work. Okay. So, and now once you have this topological recursion, it's easy to translate to some matrix model description. And the matrix model is fully fixed by either the spectral curve or the density of states. They're basically the same thing. And this density of states at large n. And if you translate using this theorem of Eynard to what the spectral curve has to be in order to compute these integrals, these intersection numbers, you find that the density of states takes this form. And perhaps the reason why we call this Virasoro minimal string and Virasoro matrix integral is because this density of states is, in fact, the universal density of states in a 2D CFT. And that's perhaps, you can see that already because you can see that through this link of the relation to the inner product, the Hilbert space of conformal blocks that we discussed before. There's a link to 2D CFTs. So in particular, that means that if you compute the disk partition function, which is something I haven't discussed, so it's the partition function in a disk with asymptotic boundary conditions, then you find that it's the Virasoro vacuum character. Okay, but you don't have to worry about that if you. Okay, but so now just once you have this density of states in the matrix model, you can just open standard papers how to compute resolvents. So the main observables in matrix models are these resolvents, which are just multiple insertions of traces of 1 over energy minus the Hamiltonian. So H is the matrix I'm integrating over. And it admits this expansion. So where GS appears as some combination of 1 over n, but I'm also taking the double scaling limit. So in the double scaling limit, I'm taking n to infinity, but also simultaneously, I'm sort of zooming in to some edge of my density of states. Because if you look at the density of states, it's not normalizable. So the number of n has to be infinite. Whereas in like a finite n matrix model, typically there's some finite support of the eigenvalues. And these resolvents are now related to in a very simple way to the worldsheet quantities. So, so here I wrote how they're related to the partition function, and the partition function are related to these quantum volumes by some operation that is known as gluing trumpets in the physics literature. But it's a bunch of integral transformations. It's very simple. Okay, and in particular, you can also use this topological recursion to directly derive a recursion relation on these quantum volumes. And it takes the following form. So basically, it's a recursion relation in the Euler characteristic of the surface, so in 2g minus 2 plus n. And if you want to compute this quantum volume of genus G and n boundaries, then what you do is you single out one boundary. And then on the right-hand side, you sum over all ways you embed 3 Hold spheres into your surface. I think this appeared in one talk earlier in the conference. And so there are essentially 3 ways of doing this. You can embed a 3 Hold sphere like this, where you have 2 internal boundaries, and the genus of the surface drops by 1. So this quantum volume of G minus 1 and n plus 1 appears. You can embed it like this so that the surface decomposes into 2 parts, and you sum over all the ways so it can decompose into 2 parts, and then you get the product of this quantum volumes. Or you can have it like this, where one of the boundaries of this 3-hole sphere is also an external boundary. And then there's some function h that appears. That is the only place where this b enters. And then you take the integral over p and p prime and convolve over it. So for people that are familiar with Mirzakhani's work, this is just Mirzakhani's recursion relation for the volumes of Weil-Petersen volumes, for the Weil-Petersen volumes. And the only difference to her recursion relation and this one is that this function h is slightly different. So if you take the b to 0 in this function h, then it reduces to the function that appears in Mirzakhani's recursion relation. But so this recursion relation still works even in these deformed cases. Okay. So that's all I wanted to say about this first theory. So let's move on to the other one. So which we call the Liouville squared string theory. Okay, so to remind you, now we consider 2 Liouville theories. Central charges are 13 plus something imaginary, and we put this ghost theory also. And again, I just put basically the same slide as before. This Liouville theory is defined by the same quantities as before. So we have the central charge, which I parameterize like this. And now, because the central charge is 13 plus something imaginary, this means translate in terms of this b parameter that the argument of b is pi over 4. So everything lies in this weird 45-degree angle. And the spectrum is, again, as before. It's just slightly more convenient. I apologize, we used a slightly different notation. So this little p is I times the capital P that appeared before. So if you paid very well attention, then before there was a plus here. And, okay. But then the DOCC formula is exactly the same as before. So again, this, and regardless, even when the central charge is complex, this still forms a crossing symmetric CFT.
I thought you said it was 1/0. Oh,
no, these
it
are
was
both
1 over for the time lag, but
this is for the time lag.
Okay.
Now there's no time lag anymore. Yeah, thanks. So this theory is really different. Okay, and so the reality of the worldsheet integral basically means that one theory complex conjugate should be the other theory. So if you take the dagger on the Virasoro generators, then they map to the other theory. And that imposes you both that the central charge has to have this reality condition that we already discussed, but it also imposes you that the conformal weights of vertex operators have to be 1/2 plus something imaginary. And that's quite interesting because that's exactly the principal series representation of SL2C. But, yeah. And again, as before, you then define on-shell vertex operators, and you can define your string amplitudes. Now they don't have a nice interpretation as a volume. We'll see what they are, so we just call them A for amplitude. And since one theory is the complex conjugate of the other theory, essentially it means that the integrands of your of this integral are just mod squares. It's also convenient to put some normalization factor. So in the physics literature, this is called lag factor, some normalization factor for these vertex operators. It just corresponds to changing the normalization of these V's. And again, it happens that this integral is absolutely convergent. Now the reason is essentially that these conformal weights are 1/2 plus something imaginary. And so if you sum them up, you get 1 plus something imaginary. And of course, when you're on-shell vertex operators have conformal weight 1, but off-shell vertex operators will have conformal weight 1 plus imaginary, which means that if you look at some coincidence limit of some OPE, where typically things become dangerous, the integral is not blowing up, but it's just oscillating, and that's enough to make it convergent. So that's quite nice. And these A's have already some properties that are completely manifest. For example, I can exchange now the 2 Liouville theories, because, and that corresponds to putting central charge to 26 minus central charge, or B to IB minus IB, and P to IP, and nothing should change, essentially. So we call this swap symmetry, because it swaps the 2 theories. Okay, and now you can go and try to figure out what the theory is. But it becomes quickly apparent that it will be something much more complicated than the previous one. So for example, you can compute the 3-point function. And the 3-point function now on the sphere will be a product of a DOZZ formula and another DOZZ formula. And again, it's convenient to put some normalization factor. And if you put an appropriate normalization factor, you get this relatively harmless looking formula. And so there's no very elementary function you can express this through. There's a paper by Zamolodchikov where he expresses, this can be expressed through some elliptic functions, some Jacobi theta functions, but again. Okay, and this is a structure that will persist. So we'll see. Oh, very good. So B squared is imaginary. So in the denominator, there's a sinh. Yeah. Yeah, and the reality conditions are such that BP is real. So there's sines divided by sinh. But yeah, the reality conditions are a bit confusing. Good. And so I already wrote this formula before. So it's a complicated integral in principle. So, and we don't have a very good way to now do some trick as we did before. So we already see the 3-point function is complicated. So it seems kind of hopeless to find some kind of intersection theory meaning of these integrals. And so what we did is to use a very different strategy, which is why I'm also showing you the second theory, because it has 2 very different lessons. So what we did is, so these A's that we get, they are very rich functions now. They have a very rich analytic structure, and they have also lots of symmetries. So for example, you get a number of poles, and those poles are associated to poles of the integrand, because the Liouville correlation function has a number of poles. They are associated to resonances in the path integral formalism. And the A's will also have a number of discontinuities. So if I promote my P's, so initially my P's were something like e to the pi a over 4 times real. But if I promote my P's to complex variables, this A's can be analytically continued. But then this integral at some point ceases to converge, and it becomes an interesting analytic function. And when the integral ceases to converge, we get discontinuities. So it's actually a multi-valued function. But one thing you can, for example, easily do is to derive the location of the poles, because they're just the location of the poles of the Liouville correlator. And it's also easy to derive the discontinuities, because the discontinuities come entirely from some place in the integral where the integral ceases to converge, which is some degeneration of moduli space. And then we also know much more things. So there are many symmetries. For example, the swap symmetry that I already mentioned. There's the obvious symmetry that if I send B to 1 over B, things should be invariant, and so on. And there's a less obvious symmetry, things that comes from the AGT correspondence in the case of the sphere 4-point function and so on. So what we did is just to systematically impose all these constraints on the function. And under some very mild assumption, which is some growth condition at infinity, it turns out that this nails down the function completely, say for the 4-punctured sphere. So we just translate this into some analytic bootstrap program. So I'll tell you now the answer, but this is where most of the work has been is buried. And I again put the danger sign because this is a conjecture. So we impose all these constraints, we make some very mild assumptions, and for the 4-punctured sphere, we have very cleanly worked this out, but this conjecture is for an arbitrary genus in N. And so there's a set of very simple diagrammatic rules. And every diagram corresponds to degenerations of the worldsheet. For the mathematicians, these degenerations are stable graphs. And so the quantum volume that we had in the previous theory actually arises in these rules, and it arises sort of as a string vertex. So if you're a physicist, you can think of these rules as Feynman diagrams of the string field theory, and then every vertex comes with some weight, which is exactly this quantum volume. So let me just explain you the formula for the sphere 4-point function. So there are 2 diagrams, essentially. You can have the non-degenerated vertex worldsheet, or you can have the degenerated one. And they can degenerate like this, or there are 2 more permutations where you permute the external operators. And then you get a sum over m's. You get a sum over single m if you have just this non-degenerate one. And you get a sum over 2 m's if you have degenerate one. So in general, you get a sum over 1 m for every component of your stable graph. And then, as I said, I said actually the other thing. So for every external puncture, you put a sine of 2 pi m bp. So we already saw that for the 3-point function. And then for every vertex, which is like every bulk component, you put the quantum volume. So here's V04, here's V03, which is just 1, but I'll just put it for clarity. And here again, you put V04, V03, and then you divide by sines. There should be actually a square here. Sorry, I forgot. But okay. And then for every intermediate degeneration like this, you also put sines for the two sides, and then you have to integrate over the intermediate momentum. So that gives you the answer. So just to drive home the point, this is the answer for the 1-point function of the torus. The one we also very carefully bootstrapped. So here you get the 1-point function of the torus, the quantum volume, here divided by the sine. You get a sine for the external boundary. Similarly, here you get a sine for the external boundary. Here you get V03. This is one degeneration, and you get an integral over this sort of loop momentum that runs here. There's also a factor of 1/2 here because this diagram has an automorphism factor of 2. Okay. So again, you might be in panic that this is kind of sketchy. So what we did is to just, again, put it on a computer and numerically check for some sufficiently random values of the momenta. And indeed, we get a nice curve that seems to match very well with this prediction. But now we improved the numerics, so now we have error 10 to the minus 5%. So it's pretty good. Okay, so you can put this for any genus and n that you want. You get some very large number of graphs. So for example, this is the answer for genus 1 and 2 points. There are 5 different stable graphs. Some have automorphism factors, some don't. Okay, but once you have this formula, it's easy to translate to dual matrix integral. So now this dual matrix integral will be a 2-matrix model, and it's characterized by this spectral curve. So this again follows by using these theorems of Einard, who told us how to compute, who told us how this topological recursion with respect to spectral curves works, and then you just have to go through his theorems to translate these things to spectral curves. And the leading density of eigenvalues in the first matrix takes this form, which looks very similar to the minimum model case, the PQ minimum model case. The difference is that now there's not a sinh, but there's actually a sign in the density of states. So there's the density of states first goes up, and then at some point goes down again. But where it goes down is part of the non-perturbative definition of the theory, which I don't have time to go into today. Okay, so some comments on the spectral curve. It's a bit of a weird spectral curve, so it admits this rational parameterization. So remember, B has a funny phase, whereas in the minimum model, B is real. So this has formally, well, you can think of it as having either infinitely many nodal singularities, or if you blow up the nodal singularities a little bit, it has infinite genus. And it also has infinitely many branch points. So in the topological recursion, you have to sum over all the branch points, which are points where x prime is 0. So there are infinitely many of those, but still topological recursion, which is usually formulated for a finite number of branch points, it converges absolutely, so we didn't worry about it too much, and it's still well-defined. And again, you can repeat the same exercise as before, and you can translate the topological recursion that you get for this 2-matrix model directly to a recursion relation for the string amplitudes. And you have to stare very closely at the slide to see the difference to the slide that I showed you in the Verzor minimal string case. So if you didn't spot it, the difference is that there's an additional A03 here. So the recursion relation is precisely the same, except I replaced A by V. But because now the sphere 3-point function is non-trivial, I also need to multiply the thing on the right-hand side with the sphere 3-point function that I took out. So it's quite remarkable that even though the theories are sort of much more complicated, the recursion relation is basically the same. Okay, so I have like 3 or 4 more minutes, so I'll probably make only 1 or 2 more comments. So one other way to understand the worldsheet theory is to map it to some semi-classical gravity. And this applies to both theories, both the Verzor minimal string and this Liouville square minimal string. And there's a well-known field redefinition that was discussed by Seiberg-Sanford and Mertens-Toraci that maps this worldsheet theory to a theory of dilaton gravity. So because basically Liouville theory is a theory of two scalar fields, and you can take linear combinations of these scalar fields, and one linear combination will be the dilaton, and the other linear combination will be the Weil factor of the metric that appears here. And there is some dilaton potential, which is sinh of b squared phi. So in the VMS case, the Verzor minimal string case, this b is real, so this is indeed a sinh, whereas in the other case, it will be a sine, because b squared is imaginary. And now you can understand semi-classically why one theory is so much more complicated than the other one, because in the sign potential for this Liouville square string theory has infinitely many vacua. If you solve the classical equation of motion, they tell you basically that phi is constant, and phi is such that the derivative, that the potential of phi star is 0, where phi star is a classical solution. And so for the sign case, for this Liouville square string theory, you get infinite number of solutions which are labeled by some integer m. And if you perform semi-classically the path integral, then you figure out that this m that appears here is precisely the m that appeared in our formulas before. So you can connect it with a semi-classical description. And one thing that is quite interesting is that actually half of these semi-classical saddles impose that the curvature of the metric is constant and negative, and half impose that the curvature of the metric is constant and positive. So half of the saddles you can view as ADS2 solutions, and the other half you can view as DS2 solutions. So it's quite intriguing that this is a theory that if you view it semi-classically as a 2D theory of gravity, it involves both de Sitter and ADS vacua. Let me skip this. And final comment, yeah. So this whole story that I told you is only on the perturbative level. We also looked at the non-perturbative level. You can see that there's non-perturbative corrections because the perturbative series that sums over the genus is an asymptotic series. And you can work out also non-perturbative corrections to these volumes that are resummed over the genus. And for example, in the last couple of years, there was lots of progress in understanding how to compute these non-perturbative corrections from the worldsheet. From the matrix model, we already knew how to compute them. And basically, the leading non-perturbative contributions, say to this quantum volume V, or also this A, both work, comes from putting some boundary condition in the worldsheet theory, which is like an instanton, a ZZ instanton-like boundary condition, and you put any number of basically, so these boundaries of these open worldsheets, they end on these boundary conditions where you have the ZZ instanton. You can put any number of disks here. You can put any number of annuli, so you get the exponential of those. And then you put some number of punctured disks, one for every boundary of vertex operators. And it was explained by Ashok Sen how to compute these quantities because they're naively ill-defined in the string worldsheet theory, and that requires some string field theory. And essentially, when you do this computation, you can compute this leading non-perturbative contribution. It's slightly ambiguous, so it has a plus-minus sign ambiguity, which depends on some choice of contour in the string field theory field space. But what's remarkable is that you can also match this leading non-perturbative correction to the leading non-perturbative correction of the matrix model computation. And we had one talk earlier in the conference that when you know this kind of data, you can figure out what the large genus behavior of these quantum volumes and the large genus behavior of these A's are using resurgence. Okay, so let me just summarize. So the 2D string theory landscape is bigger than we thought. So I explained two new entries in this landscape. So a natural question is whether this is all. Can we completely classify it? So I told you these two entries which live, one of them has real matter-centered charges and lives here. The other one has this funny complex matter-centered charges and lives here. And you can think of them as being sort of irrational cousins of the usual minimal string theory. Both of them admit still matrix models or two matrix models use. And this Liouville string for the physicists, I think, is interesting because it gives you a rigorous model of 2D quantum gravity, which involves de Sitter vacua as well as anti-de Sitter vacua. So thank you very much for your attention.
questions?
Thanks for a very nice talk. If the question is what is the 2D string landscape, we should go back and remember that the topological B model was mirrored after bosonic string. That's the way Witten formulated it. So in some sense, topological B model is a model for bosonic string.
Yes.
It's finite. You have integration of modular space of Riemann surfaces, and everything works beautifully with no analog of divergences like tachyons. The P comma Q minimum models coupled to gravity and the JT gravity and all of that can be mapped to Calabi-Yau. For example, P comma Q models coupled to gravity are given by Argyris-Douglas singular points of Calabi-Yau. Self-dual string at C equals to 1 at self-dual string gets mapped to conifold and its deformation and all that. So it seems like the whole model that we're talking about gets mapped to Calabi-Yau paradigm, namely topological B model and Calabi-Yau threefold, and that's could be an answer to what is the 2D string landscape. So it is the space of all these models. Now, some of these don't look like conventional space-times in 2D, and that's fine. In other words, sometimes the BC ghost is not decoupled from the matter sector. That happens in the context of compact Calabi-Yau. So the general question of what is bosonic string should certainly include all of these topological B models, including the compact Calabi-Yau, which is much more perhaps interesting even than these. But another aspect of it, which is your work and other related works raise, is that the kind of Calabi-Yaus you get are rather non-typical in the sense that you're getting things which are not local singularities. And so that would be, for example, you're getting sinh X and all that. So these are interesting functions. The question would be from Calabi-Yau perspective, is there anything interesting from the geometry of the Calabi-Yau threefold for these kinds of geometries? So that would be since you're getting nice objects like quantum volume of moduli space of Riemann surfaces, that should be surely an interesting canonical object. The question would be what it is in the Calabi-Yau language. So thank you for the talk.
Yeah, so, I mean, you get kind of these simple universality classes, and I agree completely that you can, from a space-time perspective, you can write them in terms of some Calabi-Yau threefold. And of course, you can consider all its deformations, and they don't preserve the factorization of the worldsheet theory and so on. I completely agree. I still find it quite interesting that there are these worldsheet theories that you can write down, and you can deform them and do all sorts of crazy things with them. But I found it personally somewhat counterintuitive that you can have these very crazy spectral curves that arise, and also the Calabi-Yaus that are allowed apparently involved in some infinite number of singularities and things like that, which is something that wasn't obvious to me that it's allowed. Yeah.
Just one other comment is that the linear dilaton backgrounds get mapped to the singular conformal theory of Calabi-Yau, where you have linear dilaton. So that map, why you get linear dilaton backgrounds like the connection bosonic string, can actually be made precise in very natural cases. So it is not just a formal similarity; they can actually map it to bosonic string.
Yeah. Thanks.
Have you dared to think about the generalization to super Riemann surfaces and super Liouville?
My collaborator, Beatrix, thought a little bit about it. So the n to 1 case should be probably doable. So the n to 1 structure constants of n to 1 Liouville theory are known, of the time-like case not, but in principle it's a doable thing.
I would think that n equals 2 or 4 would be even easier.
Potentially.
Yeah,
well, Edward and Joaquin told us how the n to 2 JT gravity is solved.
Okay.
So at least the semi-classical limit of this theory should be known. But I agree, it will be interesting. And in particular, the n to 2 structure constants have not been written down explicitly.
Yeah, I guess my question is somehow relevant to what Kumran just asked. So when you say this theory can be viewed as some JT gravity kind of thing, you mean the gravity theory on the worldsheet, right?
Yes. Yeah.
Okay, so from the target space point of view, I should think of some string propagating in the target space. I mean, is there any target space theory interpretation or some string field theory formulation like the topological B model, right? You have the Collider-Spencer theory to
Yes, that's right.
describe all these things. Do you have something maybe along those lines? for this theory?
Yeah, I mean, you can, what Kumran said, I think directly applies. So you can make a target space model where you have the, could that be a threefold is something like UV plus the spectral curve is 0. And that's a target space perspective. You can also try to think about it in terms of a 2D target space interpretation, because after all, these are theories of two scalar fields. And then it looks like a kind of like a flat space in target space, but then there are these Liouville potentials. So the Liouville potentials you can think of as a tachyon background. So there's, and perhaps you can, I mean, Victor, one of my collaborators, he wrote a paper that you could view this as a cosmological background in target space, where basically infinite paths, because there's in the time direction, there's a tachyon potential, which screens the infinite past. So basically the things, these quantum volumes, you can view them as cosmological correlators in this 2D target space.
Question. In the space-time action that you wrote down with the dilaton, the potential usually doesn't have much meaning in terms of the stability of the critical points. However, the DS critical points you had were all unstable in that potential. I was just wondering if it's possible to engineer any potential that's completely DS or ADS all the way.
Yeah, that's an interesting question. So I think perhaps the lesson of this work is that it shouldn't be possible, because, I mean, people try to define something like DS-JT gravity, and that leads to pathologies in a dual matrix model. So it doesn't seem to be a well-defined theory. This one does seem to be a well-defined theory, but I cannot exclude that there's a model that just has DS.
I see. Okay, yeah. Thank you.
Thanks for the talk. I wanted to ask, how do you fix this possible double periodic ambiguity in the structure constancy in this C equals to 13 case? Can we get some other CFTs with a little bit different structure constants, which will be similar to this one?
Sorry, just to understand, you want some worldsheet CFT which has different structure constants at the same center charge?
No, I'm saying that DOZZ are fixed by two periodic conditions, and if B squared is purely imaginary, in principle we can multiply it by some doubly periodic function. How do you fix this ambiguity? For example, how do you distinguish between C less than 1 or C greater than 25 formulas?
Yeah, thanks. I understand. Okay, yeah, so this is one consistent answer, that the analytic continuation of the Liouville theory of center charge bigger than 25 and real. So there are these difference equations that you probably have in mind. They have a unique solution, and then if you analytically continue, it will still satisfy crossing. If you just sit somewhere in the complex plane and you do this kind of Teschner type of bootstrap of the DOZZ structure constant, then indeed there's this ambiguity. But that's not sufficient to get a crossing symmetric CFT. So because that is just a part of crossing symmetry. So you still need to impose that the full 4-point function is crossing symmetric. And I don't know whether there are other solutions. To my knowledge, that's not known. And this is the only known solution. But it might very well be that there are other solutions to this bootstrap problem.
But at least there is C less than 1 and C greater than 25.
There it's unique, yeah.
Are you taking a product of one kind and one of another kind, or they're the same?
In this first theory that I showed you, this Virasoro minimal string, there's one where the center charge is less than 1, that has a unique solution, and the center charge is bigger than 25, which also has a unique solution. In the second theory, it might potentially be possible that there are other theories. I don't know.
Yeah. Thank you.
Yeah, thanks. That's a good question. So they persist to a certain degree. So basically, saying that it's elliptic, you can say that the difference operator in B annihilates the function on like any of the external momenta. what happens, say, for the 4-point function is that the cube of the difference operator annihilates it. So that's sort of analogous to saying it's a quadratic polynomial. So because if you have a quadratic polynomial, then the third discrete derivative is 0 on it. And so that is the generalization to a higher point function. And so at arbitrary g and n, it's like the dimension to the modular space plus 1 or something, power n.
If there are no, there is another.
Thanks for the talk. And you mentioned that the Liouville squared string provides the theta vacuum, right? And I'm wondering if this vacuum is stable or something metastable that will finally decay to something else.
Yeah, so that's a sort of Lorentzian question. So here I treated the theory as a Euclidean quantum gravity. So I don't quite know how to answer your question. One thing I can answer is that if you look at these kind of amplitudes that we had, so they allow, say, transitions from de Sitter vacua to anti-de Sitter vacua because they involve these kind of components where here you can have a de Sitter vacuum and in this other component you can have an anti-de Sitter vacuum where, like, say, this M1 is odd and the M2 is even. That's a saddle point of the path integral where you have partly de Sitter and partly anti-de Sitter. So they can transition into each other, but also ADS can transition to DS and the other way around. So perhaps that answers your question. Yeah.
There are no more questions. Let's thank the speaker again. There is an announcement now.
Yeah, before we go for coffee, just a small announcement. At CISA this afternoon at 5 o'clock, we're having the Dennis Sharma Memorial Lecture that's being given by Edward Witten. The event is being streamed, so we can potentially, well, we will try to stream it in here for those of you that would like to watch that. There is one issue, though, that there's apparently some building works that are going to, because we're doing lots of renovations in the building, and there's some building works which are going to commence sometime after 4:30, and we don't know how noisy it's going to be. I mean, these things happen, but the link, you know, we can also provide the link for those of you that want to, you know, you can watch it elsewhere, not in this building if it's too noisy. The other option is to, the lecture is open to everyone, so the other option is to go to CISA, for which one can go by bus from here, taking the number 6 or number 36 bus, and then on a reasonable day. Or, you know, people can also ask at the info point or just, you know, call some taxis if they really want to go there in person. And we'll provide a bit more information about the buses a bit later on. Is there anything else to add about that? Okay, yeah, so we can go for coffee now.
Okay, we will reconvene at 11:30.
Questo...
Oh, hello. Yes, I'm the next one. Just check things how they work.
Okay, we have somebody in the director room.
How they're doing it, you mean?
just point at this?
Yeah, so this goes forward and backward.
And you can just point directly here? Oh, wow.
And you don't have to point here, you can put wherever you want. There is an accelerometer inside, so it doesn't matter where you point.
Oh, I see, okay. And then you just go left and right, okay. Okay, thank you. Easy.
Hello, hello.
Yeah.
Actually, I like your comments throughout this conference.
I cannot keep quiet, that's my problem.
But they're always in a very good spirit of...
These people are doing so many detailed calculations, all we can do is some general comments from the history of a few decades ago. We were doing these kind of things. It's quite made, a lot of progress is made. Forward, regardless of old folks like us, whether we catch up or not.
25 years ago.
Not proven that.
But we need to tell the...
It's in the last session today.
This is what Pavel told me. Because another option, I thought, no, the only, I thought yesterday that it was in connection with the contributing talks. Oh, okay, we have this. By what? Then it turns.
Yeah. So there's theory 1, where the center charge is bigger than 25. And the center charge is less than 1. And here you use the structure constant C. And here you use what Limbaugh and Santagara call C hat, which is roughly 1 over C. Okay. Okay. And then, so this is theory 1, and the product in particular is essentially 1. So the three-point function will be 1. And then there's a second theory where this is something like this. And then the other one is 30 minus IS. And here you use the structure constant C and C, not C hat. So it's the, well, this is the C of B and this is the C of IB. So, because that is just, so this means that the center charge here corresponds to some B, and this corresponds to IB. But these are both the ordinary Liouville structure constants.
I see.
In particular, the product will not be 1. The product will be this complicated three-point function relation.
Yes. And what happens if you take the same structure constants, then...
The charge needs to be 26, so you can't do that.
If you take the product of this structure constants, it becomes periodic function, right?
Yeah, it becomes an elliptic function. With the correct, so some numbers, you need to normalize the vertex over this in particular way.
But what if you apply this elliptic function just by 1?
Sorry?
What happens if you replace this elliptic function by 1? Because naively, it seems that from the point of view of the recurrence relations, it should also be a solution. Cannot be some adequate...
Yeah, so basically this is this. So one thing that happens is that, so you maybe know that this one, we cannot analytically continue away from this region. Because there's like some infinite number of poles, and if you do the OPE expansion, you cannot analytically continue this away from real C hat. But one thing that happens once you put them together and you integrate over modular space, you can analytically continue, because all the singularities cancel out.
Wait, this function can be continued everywhere except this.
Okay, the three-point function. Okay, but so if you look at the four-point function, so this one, so the three-point function you can analytically continue, it's not a problem. But the four-point function involves some integral over P of basically C hat and some conformal block. Okay. So, and the way this integral works is, so this P goes over, say, the real line, but you actually need to slightly shift, so there's poles on the real line everywhere. There's actually a dense set of poles on the real line. And the proposal of Limbaugh and Santacara is to move the contour slightly up by some IAT. It doesn't matter where you put it up or down because of reflections. But now you try to analytically continue this in the center charge, and what will happen is that these dense poles, the dense set of poles that lies on the real line, it spreads to the whole complex plane. And then there's no contour over which you can integrate anymore. So this thing doesn't seem to admit an analytic continuation. So basically the location of these poles are something like PD, inverse or something like this, where P and Q are integers. And so when B is real, this is a dense set, and B is irrational.
But you multiply such conformal blocks and integrate.
Yeah. So this is not known to have an analytic continuation. But if you multiply it with the other Liouville four-point function and integrate it over the cross ratio, and look at the string theory amplitude, then it's just polynomial, and you can analytically continue.
So it is somehow healed by this three-point functions. Is it true?
Sorry.
Is this problem somehow healed by this three-point functions, which equal to some elliptic function or not?
Yeah, so for three-point functions, kind of not a problem, but once you look at the four-point function, then there's this problem that you cannot analytically continue.
Is it essential in this integral that you multiply by this product of three-point functions, which were chosen in this particular way? Do they somehow cancel this poles?
The poles, no, so the integrand has a number of poles. So there are several integrals we're doing, right? There's an integral that is this integral over p that defines the 4-point function. So that has an integral here. And the integrand has a number of poles. It's actually a dense set of poles in the real line. This 4-point function also has some poles, but they're located in different. So the poles here have nothing to do in principle with the 4-point function. Okay, and also some of those poles come from C hat, and some of those poles come from the conformal graph. And now, what is your question? So it's not how to analytically continue this thing?
No, my question was that to define CFT, we need to choose some so-called functions. Yes. The question was why is it choice such that you took the same function from C greater than 25, multiplied them and obtained some elliptic function. So why could not you say that you took another so-called function from for example, this CFT, and in this case, the product will be equal just to 1.
Yeah, but this CFT doesn't exist when the center charge is bigger, not less than 1. That's the point. Or at least nobody constructed it.
You're saying that even though you can write some formal solution of
Okay. Sorry.
Even though you can write some formal solution for the second situations, it does not correspond to the actual CFT, right?
Not necessarily. Yeah, we don't know that. I think it doesn't.
Okay.
But I cannot exclude that there's some other solution.
Oh, this will be no.
Unmute? Yeah.
Okay, welcome back for the last talk of the morning. Khurrum Vafa is going to talk about Cardi formula and the black hole entropy.
Thank you. Thanks to the organizer for organizing this amazing conference and also giving me a chance to give a talk here. I'm going to talk about a work I've done recently with Indranil Halder and Kai Chu related to an old story. The story is about how do we account for the black hole entropy and what is the relation of that to the Cardi formula. So microscopic explanation of Bekenstein-Hawking entropy is one of the first concrete evidences that we found in string theory that said that we perhaps have the right ingredients in string theory to describe quantum gravity. It accounted correctly for the black hole entropy in particular. But the typical way this gets done is a little bizarre, I would say still. At least the typical way people have done is a little bit funny. Namely, we relate the black hole to a black string. It's not a direct thing. It's always an indirect path. And the typical way is one considers a theory if you're interested in a d-dimensional theory with black holes in d dimensions, you first of all find the theory in one higher dimension. So you go to d plus 1 dimension and find the theory which equivalent to the theory you're interested in upon a circle compactification. Then you realize the charge states that you have in d dimension, the black hole that you're interested in studying in d dimensions, to the states of the wrapped strings wrapped around the circle in the one higher dimensional theory. So you choose the string carrying various charges and in addition can wrap around the string and also have momentum around the circle. And with momentum and the wrapping around the circle together with the extra charges, you can potentially account for all the allowed charges that you might have in the lower dimensional theory. And then in the limit that you are getting the large amount of momentum around the circle, you can use the Cardi formula if you know what is living on this string. In particular, all you need to know is what is the central charge of the string. You can predict how many states live on it, at least asymptotically when there's a large momentum, using the usual formula that Cardi found, that namely you find the fact that by modular transformation, the partition function gets related to the q to the minus c over 24. And using that behavior, you can estimate the asymptotic growth of states. And you get a formula which accounts for the black hole entropy in this way for large enough n. So that is the typical way that the accounting of the black hole entropy has been done in string theory. As you can see, it's a little indirect. And a bit strange why a string shows up. And the question we were curious is whether or not strings always shows up in a black hole situation, or is it just the artificial feature of some of the examples that people have studied. So the C will depend, the central charge of the string we're talking about will depend on the charges it carries. And in some cases, one can do better. And we can actually account for the exact degeneracy of the black hole entropy index, not just asymptotically. So here I have to clarify what do I mean by black hole entropy index. So black hole entropy, you just count the number of states of black hole. But black hole entropy index is in the context where we have a supersymmetric black hole, and there's an index which you can compute, which is invariant, which is simpler to compute. Now, a priori, the black hole entropy index is in absolute value smaller than the black hole entropy because you have some plus or minus cancellations potentially. Typically, what we find is that there are no cancellations at least to leading order, and this works nicely, and we can get our answer. Now, this is not always correct. We have counterexamples where this does not happen. So here, today, I'm only going to talk about black hole entropy index, where things can be actually computed in a relatively straightforward fashion. And most of the times, that actually agrees with the black hole entropy, at least to leading order. And in some cases, you can actually compute this exactly, for example, in the context of if you take 5-dimensional black holes and you consider M theory on T6 or K3 cross T2, as were the first kinds of examples people studied for the black hole, you find that you get things having to do with the elliptic genus of symmetric products of products of K3 or T4. And this kind of thing people have studied and give you the right entropy for the black hole leading order as well as all the corrections. And they work beautifully well. So the next question, of course, once you study these cases, does this work for arbitrary Calabi-Yau threefold? Is there a similar story for if you change T6 and K3 cross V2 and replace it by arbitrary Calabi-Yau threefolds? Now, in fact, for Calabi-Yau threefold, more generally, there are other ways to, at least in principle, compute a black hole entropy without appealing to a string. So there, you don't need a string a priori to get to the black hole. And the idea would be, if you compute topological strings, topological A model, on a Calabi-Yau threefold in particular, you get a count of BPS degeneracies of particles in 5 dimensions, labeled by a charge Q and by a spin J. So in other words, in 5 dimension, the rotation group is SO4, and that is SU2 times SU2, 2 SU2s in it. One of them, if you're interested in supersymmetric spinning black hole, the spin can only be inside one of the SU2s. So you would ask, if you're interested in the BPS spinning black holes in 5D, you'll be asking about the charge and the spin sitting in one of the SU2s, and you ask, what is this number? And the answer is, if you compute topological string as a function of Kähler moduli T and the string coupling constant lambda, you can recapture that in terms of this structure, where the degeneracies of these BPS states ends appear, and this generating function for these BPS particles gets related to the topological string amplitudes. So if you know how to compute topological string amplitudes, you are done with computing the supersymmetric BPS black holes in 5D, at least the ones you get from Calabi-Yau, for arbitrary charge and spin. Now, you might say, okay, suppose I don't know how to calculate the charge, the spin part, but I just sum over all possible spins. Do I get the right answer for just the charge dependence without caring about the spins if I added up all the spins with a -1 to the fermion boson degeneracy and add them up? And the answer is no. That's one of the cases where the index cancels quite a bit. So you get the wrong leading behavior. So you really need to distinguish which spin you're talking about to get potentially the right answer. And then it becomes very difficult. For example, if you are interested in this genus 0 answer of topological string, which you can easily compute using period of mirror symmetry, you would be able to compute the charge, but not the spin. And the spin would be you're summing over all the spin with the plus or minus signs, and you get the wrong behavior. You get the growth of the BPS black holes would have gone like exponential in charge rather than charge to the 3/2. So you get the wrong power even, leading order. So that's an example where the leading order would not have worked. So you really have to distinguish the spin correctly to get potentially the right answer. And then that becomes difficult. So if you have, for example, a particular genus calculations, 0, 1, 2, etc., if you go down to higher genus, and then there's a charge, so you get the charges contribute to a given charge contributes to all genus in principle, but for a fixed charge, after some genus, it starts after you get some kind of no contribution up to a given order, and then it starts. So if you're interested in low enough charge, you can stop by computing topological string up to a given genus. So therefore, by finite computation, you can get the answer to a finite charge if you're interested in doing it. But the asymptotic formulas we're interested in only starts for large charge. So therefore, to get the full answer, you have to do all genus topological string answers. It is a bit embarrassing that after all these decades, we still don't have a single Calabi-Yau, compact Calabi-Yau, for which we know the full answer for topological string, for which we can do this check. We have answers for non-compact Calabi-Yau, and in particular toric ones, but it does not apply to the case of black holes that we are interested in. So we don't have the techniques to do it. I mean, there have been beautiful progress in this direction by Albrecht, for example, and his collaborators, where they can push the computation of topological string to a very high genus. 50 was a while back, now the record is, I don't know, 90 or whatever. So you can really push it up by various techniques and asymptotic studies of topological string amplitudes, but not really much bigger. I mean, we still are not in the asymptotic regime. Nevertheless, people have used this large enough, quote unquote, value and checked these formulas, and they kind of work. That is, you get kind of the expected supergravity answer if you just charge 100 or charge a 50 or whatever, which is close to being big. And so it kind of begins to work. More than that, they actually looked at some people, in particular Indranil and his collaborators, look at even the spin dependence. And in that context, you have a spinning black holes and spinning black rings. And the description of the black ring entropy and the black holes are not the same. There's a different behavior. And they also saw features of that using topological string computation. So the topological string computation is quite an interesting avenue to try to kind of connect with extremely interesting physics, including black holes, black rings, and so on. Still haven't done. So it gives more motivation to try to find ways to actually compute topological string amplitudes for compact Calabi-Yau threefolds, which we still don't know how to do. So I already mentioned some of the progress that has been made here by various groups. However, there is one particular class of Calabi-Yau that you can do another trick. And that is for M-theory on elliptic Calabi-Yau. If you're interested in elliptic Calabi-Yau, in this case, the BPS states, of course, as general case, for any Calabi-Yau, the BPS states are M2 branes. But for elliptic Calabi-Yau, you can push it one dimension higher. In this case, you can push it to F-theory in 6 dimensions. In other words, take F-theory on elliptic Calabi-Yau. You get the theory in 6 dimensions. And this gives you a way to realize the strings in 5D, which corresponds to M2 branes, the BPS black holes in 5D to a string in 6D, which is wrapped around the circle. And that is the technique that people have used. So let me review how that works. So suppose you have an elliptic Calabi-Yau threefold with a base B and an elliptic fiber E. So the F-theory compactifications, you have, it's the same as usual, compactify on a B with the 7 branes, PQ7 branes, which capture the monodromy of the coupling constant on the base. And so you have roughly this picture. You have a base, and you have an elliptic fiber. And then you look at the 2-cycle classes inside the base, for example. And you can wrap D3 branes of type 2B along these cycles, 2 cycles, and that gives you a string in 6D. So if you take this theory, which is in 6 dimensions, and wrap it around the circle, and wrap a D3 brane around the circle, then you get a BPS black hole in 5D corresponding to elliptic threefold that corresponds to this one. So if this is the picture for that, so you have the base, the elliptic fiber, the 2-cycle class. You multiply it by a circle, you go down on a circle, you wrap a D3 brane around this base, which becomes a string, and you can wrap the string around the circle and give a momentum n to it. So you have a winding and some momentum n, and that gives you a particular class of strings that you can, BPS states in 5D, that you can in principle relate to properties of this string. These string states with n units of momentum correspond in the M-theory dual to M2 branes wrapped around the cycle C. So in the elliptic threefold, you have a 2-cycle C, but you also have the elliptic fiber. So the momentum gets related to the class in the fiber that you're wrapping around, so n times the elliptic fiber. Now, if you calculate the central charge of the corresponding string, it depends on the self-intersection of the cycle as well as the C dot C1, the first Chern class of the base. So you get a formula for the central charge of the string. And if n is large enough, if the momentum is large enough, you can compute the degeneracy of states, and you get a formula like this for the entropy of the black hole, which is indeed agrees in the large n limit to the expected formula for the BPS states. Now, this is not the most general charge configuration for M-theory and elliptic Calabi-Yau. In general, there would be additional classes, which is not captured by the base. In particular, there could be 2 cycles, which correspond in the M-theory picture to the U1 charges that emerge in the corresponding 6D theory. So there are 2 cycle classes. I'm dividing the 2 cycle classes in the Calabi-Yau to the elliptic class and to the base one, and then these p alphas are in the singular fibers. So you get extra U1 classes, And these correspond to the Mordell-Weil rank of the elliptic fibration. So you get some number of extra U1s in this scenario, so you can get the charges in all of these classes in the 5D. But in the context of the string context, you just wrap around the given cycle, and you have a momentum around it, around the circle. These classes correspond to the charges that the string carries. So in other words, the string will carry on the worksheet extra U1s, U1 to the power of the rank of the Mordell-Weil group. And using that, you can actually compute, again, the degeneracy of BPS states. More precisely, you can define, so there's a U1 to the rank of the Mordell-Weil group, and then you have a level of these U1s given by this triple intersection where S alpha and S beta correspond to the dual 4 cycles to the corresponding U1 singular fibers. And the C hat is the elliptic lift of the 2 cycle. In other words, the 4 cycle corresponding to the total space of the elliptic fibration over that cycle. So the triple intersection of these four cycles gives you the level of this U1 to the power of the Mordell-Weil group. So this K appears in as the level on the string for the U1s. And so the formula that you would do is, as a canonical thing, if you have a large momentum, you just subtract the corresponding charge, the corresponding dimension that goes to the corresponding charge. So if you have a charge carried by L alpha, you get the shifted dimension, which is L squared over 2K, which is this matrix multiplied by the L's. That just gives you the dimension of the U1 portion of the conformal dimension. And this is the amount left over, which gives you, again, the correct Cardy formula. So the Cardy formula gets shifted by this amount. And yeah, one can check, and again, it works beautifully. So there's no problem. So we have a formula which works in the limit of large N. Large N meaning large momentum number. So this is a nice picture, simple picture. So then you can ask, what is the gravity picture? What are we predicting? What are we trying to match this with? Well, the supergravity picture is actually a very rather elegant formula. So the idea is very simple. You take a charge class, so you're now thinking about M theory on a Calabi threefold, and you have a 2-cycle characterized by a charge class Q. So you find the Kähler class on the Calabia, whose square gives you that 2-cycle charge class. In other words, if you take the dual to the Kähler form, it would be a 4-cycle. The intersection of that 4-cycle should correspond to a 2-cycle, which is the charge you're trying to get. This does not always have a solution. So when this does have a solution, you expect to have a macroscopic BPS supersymmetric gravity black hole. Sometimes there's no such thing, and that's perfectly allowed. So these would be a prediction of what will happen. If there is such a solution, then you have a black hole entropy. And the entropy is simply given by, for that charge Q, you have found the K, you cube the K and integrate over or do the triple intersection of that Kähler class, and you find the entropy in this formula. So it's a relatively simple formula, and from this you see that the entropy scales like charge to the 3/2, for example. Now, notice that another way of saying this is you can say the same formula in a different way, which I think is very useful to think about. If you fix a particular charge in the Calabia, you choose the Kähler class on the Calabia, which minimizes the volume of that class, subject to the total volume of Calabia being fixed to, let's say, 1. That value of the Kähler class is what's called the attractive value, which means that as you solve the supergravity equation, as you approach the horizon of the black hole, the Kähler class changes from infinity, from wherever you started with, to this attractive value. And near the horizon, when you do the computation to get the entropy, you get this formula. So that's basically the idea of how you get this formula. But mathematically, it's a very simple formula. The idea is that you have this K and you have this Q. This is a prediction that you will have holomorphic cycles which are ample enough, that in some sense movable, that you can actually calculate their entropy and get non-zero answers if K squared is equal to Q, that you have such solutions. Now, let's go back to the case of F-theory we were talking about. In the case of F-theory, when we were talking about large n corresponds to the class of the elliptic fiber. And if this class is large, if you want to minimize the volume, you want to take the elliptic fiber to be small because you have a large winding around the elliptic fiber. And therefore, the large n limit geometrically in the F-theory language means elliptic fiber shrinks to 0. So the Cardy limit for the elliptic vibration in the context of matching to M-theory black holes means take the elliptic fiber, go to 0 size. That's basically the upshot of this kind of calculation suggests. So this comparison for microscopic black hole entropy for M-theory on elliptic Calabi-Yau is satisfactory. However, this does not cover the non-elliptic ones. And this had been bothering me for many years, many decades. And I always heard people say, oh yeah, black hole entropy are always related to strings. I would say, no, there's counterexample, M-theory and quintic. I will always give this example because it's not elliptic, and I didn't know how to do it using strings. So M-theory on quintic, the famous Calabi-Yau, the basic Calabi-Yau, does not have such a description, and therefore, what do you do? So again, the question is, you take from 11 dimension down to 5 dimension on the quintic. M2 branes can wrap about 2 cycles in the Calabi-Yau. The usual calculation of topological string counts these holomorphic curves. There's a BPS formula predicted by supergravity. Can you match these? That's the question. And the question is there any string somehow looming around the corner somewhere? That was the question we were trying to understand. Okay. So the basic idea is that, well, even though quintic is not elliptic, it's connected. Oh, the Calabi-Yau is presumably all connected in some form, and therefore you can go to an elliptic one. Do a geometric transition to connect the quintic to elliptic one and use the string there. That sounds like a strange construction. We're talking about quintic. Why do you go to elliptic one? That's a bizarre thing. Well, it is a bizarre thing if you're interested in the exact black hole BPS entropy, but we're interested in BPS black hole entropy index. And therefore, we may have a chance. If you're just talking about the index, the question is, can we make a transition which respects the index, that the index does not change? That's the question. If we can do that, then there is no difference between the quintic and elliptic threefold if we can make such a transition. And then we can try to use the elliptic one and do the calculation there and say that this does not depend on the deformation, and we are back to the quintic, and we are done. That is the strategy. Is that clear? So we're trying to see if this strategy works. So the idea is, you look at the quintic, you solve the attractor equation, which is k squared equals to q. You deform the complex structure of the quintic, and it turns out, indeed, there is a deformation of the quintic, where you go to a degenerate complex structure, for which you get a degenerate elliptic vibration over a base, some base. But actually, this is a genus 1 vibration. It's not elliptic vibration with a section. So this is sometimes called a genus 1 vibration. So you can do this relatively easily. And then you can hope to say, okay, so we have gone to the place we want to be. The trick is that deformation of the hypermultiplet or complex structure does not affect the black hole entropy index. They're decoupled, so you don't need to know about them. Their degeneracy and all that don't talk with each other. And therefore, you can reliably calculate it there. So this leads to identifying the leading charge behavior of the black hole entropy to the elliptic genus of a particular string. Namely, what does that mean? Go to the single elliptic Calabi-Yau threefold, find the configuration of charges that you're interested in whose attractor value is the singular Calabi-Yau, and use that to calculate that of the quintic. However, we can say it a bit more precisely what this means. In fact, we can do it in the following way. We don't need, in other words, the attractor value that I was talking about was only true for large charges. we can actually compute the exact values for any charges in this way. Namely, you study, suppose you go to a calabiao that you know how to get, that you know how to count, and let's call the corresponding states, the charges, the degeneracies of the charges, let's call A and Q. I've ignored the spin for now. So you have extra charges now because you have some other charges that wasn't in the game when you made this geometric transitions. You lose some of the charges, but that doesn't matter because it's like Higgsing, and you're interested in fixing the number of BPS states of a given charge Q where you don't care about the other charges. Said differently, if you were trying to compute the topological string amplitudes from one to the other, you get some extra parameters on one side that you're degenerating to one side, which you don't care about, and you compute the topological on the other side. That's another way of saying it. So therefore, you can calculate the topological string amplitudes by this transition if you wanted to, if you could do it on one side. However, here you have to compute all these charges, and therefore this will correspond to computing not just one string, but a collection of strings. So we map the problem of counting the BPS black hole degeneracy of the quintic to the calculation of BPS degeneracies driven by a collection of strings that we have to sum up to get the full answer. So we are really suffering now. We are not just one string, but a collection of them have to be in the game. Nevertheless, let's proceed. So we are getting a hard problem, but anyhow, we are forging ahead. We find the surprise, which may have been anticipated. You see, the attractor value for the elliptic threefold corresponding to the point of the transition to the non-elliptic threefold is far from the 60 limit. In other words, you can deform the quintic to become elliptic, but the elliptic fiber and the base sizes are roughly the same size at the time of transition. Now, you can choose a different charge whose attractor value would have been elliptic fiber shrinks, and the base is large, and then you can use your Cardy formula. But the limit you're ending up is not that limit. The transition point, the elliptic fiber is not small anymore at that attractor value, and therefore you have not so large an n compared to the central charge. So in this limit, we cannot trust the Cardy formula for the asymptotic growth of states. In other words, one of the hopes of this description of using string was, at least in some limit, you can actually use it to compute it. Here we got string, actually a collection of strings, but the limit of charges that's relevant for this calculation is out of this, is not in the regime that we are at. So in other words, you cannot use the Cardy formula to compute the asymptotic growth because we are not at the asymptotic value of the levels. So basically the picture is like this. Yeah, they have a quintic. You deform the complex structure to make it singular. But now this corresponds to a particular black hole charges in the elliptic vibration for which the n, the value of n and the base are not too different. And if you make n much, much larger to get to the elliptic one, you do get a description which is valid. So this is the regime where the Cardy formula is valid. But you're interested in this kind of values where n is not that large. And so it may fail. Question is, does it fail or does it not fail? Said differently now, instead of reproducing the gravity answer, we can turn it around. The gravity answer is going to predict for us the corrections to the Cardy formula if they don't agree. In other words, now we don't have any right to expect that the Cardy formula works, but we at least can turn it around and use the gravity answer to find the correction to the Cardy formula in this regime. Of course, if we knew the exact elliptic genus, if we can actually find what are the strings, what degrees of freedom live on it, and compute the elliptic genus, we are done. We don't need to take any asymptotic formula, but that's not easy to do, so we don't know that, how to do such a thing. So the strategy now changes. Instead of reproducing the supergravity answer, we use the supergravity answer to see how the Cardy formula gets corrected. So, So let's go back to quintic again. Now, a little bit more detail. So we want to make the transition from quintic to an elliptic threefold. So elliptic Calabi-Yau makes transition. There are two natural ways we can do this. One is to a Calabi-Yau, which has a genus 1 fibration. Another one is to have a genus 1 fibration together with the section, in other words, elliptic threefold. We can do both of them. The formulas are simpler for the one with the section, but the geometry is a bit more complicated because we have one extra Kähler class. But otherwise, the methodologies are not that different. I'll describe both of them. So let's do the one first of all corresponding to a genus 1 fibration. So you take, you consider a polynomial of degree 5, which is the description of the quintic in terms of 5 variables that we have. We tune the complex structure so that the equation for the quintic looks like this, where u and v are degree 1 in x, and q is a degree 3 in x. So you go to a point where you can write the quintic in terms of determinant of this equation, this matrix. So you're at this singular point. And then you blow up, basically, that point to a P2. So you define now y1, y2, y3, determinant being 0, satisfy this equation. Said differently, we are considering the surfaces, the Calabi-Yau defined inside P2 times P4 with these equations given by these weights. And the y-coordinate gives rise to a map to P2 whose fibers are Calabi-Yau 1 forms, i.e. elliptic curves. Genus 1 fibration is coming from that. So you have a genus 1 fibration over P2. As I said, this one does not admit a section, but with a little work, and I will show you the example where you can get an elliptic Calabi-Yau with a section. So we can now compare with the supergravity answer. So again, we have this formula I was telling you about, where the corresponding charge, the two-cycle charge, is n times the elliptic fiber, some two-cycle class, some U1 charges. And we want to compare this with the formula from the supergravity, which is captured by, if you fix the charge Q, you find the Kähler class corresponding to K squared equals to Q, and you plug it into this formula. That's the prediction of the supergravity answer. So, so the Cardy formula will give you, naively, it's this one that I was telling you about, n minus the shift due to the U1 charges. But actually, there's a slight shift if you want to get a more accurate formula, because the actual momentum gets shifted due to the brane charge by a term C1.c. So if you want to have a more accurate version of Cardy's formula, there's a further correction, C1.c. And C squared and the central charge, etc., of the conformal theory has been captured by the leading term, which is 1/2 C squared there, term that we have put there. So I call this S of Cardy, and a slightly more improved version of it I call S of Cardy prime. So there are two different formulas we want to check with, and we want to compare it with the supergravity answer. So we will calculate both of them. So S is a supergravity answer. S Cardy prime over S is the ratio for the improved Cardy formula compared to the supergravity answer. And S Cardy over S is the unimproved one. And we land, so you ask, what about the charge classes that you land to correspond to this singular version of this elliptic Calabi-Yau? You find the ratio of the charge in the fiber to the base is 5/21. In other words, this is not nearly close to the large n limit. Namely, the fiber and the base are roughly the same size at that attractor value. So this, we don't expect the Cardy formula to work well, which we should have had n over m much, much bigger than 1. Of course, we can look at this formula and compute this for the elliptic one for large values of n, where we know it should have agreed, and extrapolate back to the value 5/21, where we can see whether it agrees or not to this prediction. So on the following plot, I'm going to show you perhaps I should shift over, but we will see what happens to this curve. Perhaps I should go over there. Let me just show you the curve. So now you think about this as a comparison on the elliptic Calabi threefold charges, which is captured by an n elliptic class, and m is the base class. If n is much, much bigger than m, in fact, not much, if even a factor of 2 or 3 bigger, you find that the improved Cardi formula is pretty good. It matches the supergravity answer very, very nicely, even if n is a factor of 2 or 3 higher than the base charge class. The non-Cardi formula is a little less. The non-improved one is a bit worse, but still not too bad. But as you come to the value that you're interested in, and the value that we are interested in is over here, one of them actually becomes imaginary. So it's that bad. The improved Cardi formula, if you extrapolate it back to the value that would have been quintic, gives you an imaginary entropy, which makes no sense. And the non-improved one would give you some positive number, but you don't trust it. So this shows the Cardi formula fails, or more on a positive way of saying it, is you know what is the correction to the Cardi formula to compute the elliptic genus of that string for that n. So that's the way to perhaps think about this example. Now, I should go back here. You could have asked, when would it have worked? Could there have been any chance? Can we geometrically see what is the condition that the Cardi formula would have worked to leading order better than this? Indeed, there is a geometric condition, and that is why we got lucky with the first examples that we studied in the back in the days, where we had K3 cross T2 or T6. That is because the volume of these elliptic threefolds is a product of the volume of the elliptic fiber times the base. It's just a product. If the elliptic Calabi threefolds volume was a product of the elliptic class times the volume of the base, then there would be no leading correction in the into the Cardi formula, even as you came in from supergravity. So supergravity correction is precisely big when the volume of the elliptic Calabi threefold is not a product of the elliptic class times the base class. So that is the geometric way of saying what happens and what is the correction. So the corrections that become significant are precisely from non-factorization of the product to the volume to the product of the fiber and the base class. So, and that's the example we are seeing. Now, you might have thought, well, maybe this has to do with anything to do with the elliptic fibration being genus 1 with no section, but what about if there's section? You can write another one. You can improve on this. You can get the elliptic fibration with a section. If you go to a further degeneration, so you can define the quintic inside a P1 times P2 times P4. In other words, you can blow up another P1. So you introduce 2 more Kähler classes. And you basically write the quintic in this particular form. You're in a more degenerate version of it, but then you blow up P1 and P2. And you can describe it by these weights. You can describe the corresponding blow-up geometry. And you get a perfectly fine one there. And then you ask the same question, and the same thing happens again. That is, you compute the corrections. You can compute the predictions from the black hole answer, from the supergravity, from the Cardi formula to the supergravity answer, and you find that neither of them does well in the region that you're interested in. But asymptotically, of course, they work well as they should have. Okay. That is an interesting negative story, I would say, perhaps, but perhaps we should have expected. If there is no obvious string in the game, you can push a string on the problem, but it's not going to help you much. That's the lesson we are learning here. Namely, there is a string, but that's not a natural string in this context. We are forcing it on the problem. And if you do that, that's fine, but then you learn something about the string. The string is not going to teach you much. In some sense, that's the lesson we are learning here. So let me actually conclude, even though I'm a bit ahead of time. Maybe lunch is not too far away for us. So, so BPS black holes in M-theory compactification, non-elliptic ones, can be identified with the elliptic genus of a collection of strings if we could actually compute it. The Cardy formula fails, generally speaking, to capture the relevant pieces precisely because we are in a funny regime. We are in a regime where the excitation number, the level above the vacuum for the conformal theory is of order of the square root of central charge, which is nowhere near the asymptotic regime we are interested in when C is large. And that's why it fails. So we know the failure. We know how the failure can get corrected. That's a prediction we are making for that string. And once, hopefully at some day where we can compute such strings and their elliptic genus, then we can verify how these formulas work explicitly. So I think with that I will stop. Thank you.
Do you think that the introduced ratio here in any way has a relation to the recombination ratio or the charge to mass ratio?
You're talking about N over M? What ratio are you talking about?
The S Cardy over S.
Oh, not in particular, no. I mean, it's just the two formulas we're checking against each other.
It doesn't have anything to do with gravity conjecture.
No.
Okay.
In fact, as you saw, it became imaginary when I went to the charge of interest for some of them. So no, there's nothing physical there.
So have you tried for other Calabi apart from quintic? I mean,
I think this idea, I'm sure this will work in general. So there's a conjecture that all Calabias are connected. Therefore, you can connect all of them to elliptic threefolds. And I can bet that this idea generally works, that there is such a picture, but it's not going to be terribly useful if you're really interested in the leading behavior, unless you're interested in learning something about the correction to Cardy formula for that string. That's the basic
I was thinking like if one could try for multiple examples and see if there is some trend, or you can figure out more insights of the problem itself. I mean,
no, you can geometrize, as I said, we can geometrize what is that correction. You can write a formula for that correction because, as I said, it has to do with the non-factorization of the volume to the product of the elliptic to the base.
Yeah, so
therefore, that lack of factorization, there's a triple intersection formula. You can use that to find what the correction is and write it down. But understanding why Cardy picks up that correction is not easy.
Yeah, so I'm asking this because when you have multiple examples, you could see this kind of product structure for which you said that Cardy formula may go through. It may work, right? So
to leading order, but you can make it go through because the triple intersection structure is such that the volume does not pick up intermediate.
Okay, so I was asking it in the sense that when you go to some Calabia, which is having, for say, H11 more than 3, are equal to 3, going to torus case or like K3 cross T2 type of cases, then maybe you could find some explicit example where it works.
Yeah, no,
so
I mean, you can find it, but I wouldn't read much into the physics of it. That's all I'm saying.
Okay.
There's no reason it cannot exist.
Okay, thank you.
Hi. I wanted to ask about what you said about learning something about the string. So can you take this kind of correction that you get from whatever supergravity calculation and then take it back to the quintic threefold and extract some new prediction or consistency check for some count in higher genus?
Not necessarily. Well, it depends on what you mean. If I had the exact calculation done, you mean? Or just general structure of it? Which one are you asking?
I mean, if I understood what you were saying whatever you can learn from the quintic gives you a prediction which is wrong, and then you can know the correction to this prediction. So that's, if you knew the full calculation for the quintic, then you would get an answer which was correct.
Right.
But knowing only some piece of it gives you an answer which is wrong.
Right.
And so what I'm asking you is that since you have this other thing to compare to, where you compare the wrong thing and the right thing, if you can take that difference, move back to the quintic, and learn something. I mean, I think you were saying learn something about the string. Did you learn something about curve counts on the quintic in this way? And if not, why not?
Not really, because all I'm using is a triple intersection of the quintic. I'm just using the trivial fact of supergravity, which is just the 5t cubed term of the quintic, and everything is there. You're not going to learn more than that about the quintic. We are using it the other way. The supergravity is smart enough to give us a prediction for the large charge behavior. That's the magic of the Bekenstein-Hawking entropy and the duality between supergravity picture and the microscopic picture, which is very non-trivial. So this is an example of it. We can actually use that to make a mathematical prediction about what are the structure of the elliptic genus under corrections in this case. Of course, from the physics side, we want to also go backwards, namely from microscopic prediction, go to this classical geometric formula we have and try to recover it. And in this case, it's going to be hard, as I explained. So it's not like it cannot be, but I don't think we're going to learn much from it. But I do want to emphasize, again, I said it already once, but I think that the community of string enthusiasts who are mathematically inclined should put maximum effort to try to find the topological string amplitudes to all genus for compact Calabi-Yau, which we still do not know. It's embarrassing, I would say.
Yeah, thanks, Corinne, for the nice talk. I just wanted to comment that there is one setup where the black string description is very effective in the compact Calabi-Yau case, is when you're trying to count four-dimensional black holes of this D4, D2, D0 form. And those, of course, come from wrapping M5 brain on a divisor.
That's right.
And you get very precise.
That's MSW construction.
Yeah, precisely, and you get very precise control on the asymptotics. So, of course, you're asking a different question, which is to understand five-dimensional black holes.
But even there, you don't know how to do it with D6 brain, for example. So the existence of a...
Well, you can actually use row crossing to relate these
Perhaps.
D4 indices to D6, and then get information
then indirectly connected to a string. Then indirectly connected to that string that you have.
Yeah, precisely. So,
so these are somewhat along these lines, that in some problems, there's a natural string around. In some other cases, you can relate it to some string, which is what we were trying to do here.
Yeah. So of course, these row crossing elements are very complicated. There's a dense set of rules, but you can use them effectively.
No, I mean the string examples. There are plenty of beautiful string examples which give you the black hole entropy. That's not to diminish the importance of string picture for black holes.
The elliptic genus is an index, while the Cardi formula is a degeneracy. In general, they need not be equal. So when will you expect the index to be equal to?
Oh yes, I think I already mentioned that. So when the elliptic Calabi-Yau volume is equal to the volume of the elliptic fiber times the volume of the base, I expect the leading terms to agree.
Okay, thank you.
Okay, thank you for the nice talk. So if you take this three-section genus 1 fibration for the conifold transition, what the topological string actually encodes is not the elliptic genus, but a twisted elliptic genus, right? So our first question would be...
Sorry, what do you mean by it's not elliptic genus, twisted elliptic genus? What do you mean?
Well, from the F-theory perspective, you've turned on a discrete Wilson line by going from F-theory to M-theory, and this shows up in the elliptic genus by taking the trace over the twisted Hilbert space.
That's what you mean, okay.
Yes, so I wanted first question to ask how that enters the story, and second, in the same modular space, you also have a mum point which is associated to the twinned elliptic genera, and if this gives you a different result, or if you have looked into that.
The Mordell-Weyl class is related to that Wilson loop that you're talking about. So that ELF correction is important for calculating it correctly when you put that phase.
But in the genus 1 fibration, you didn't have a non-trivial model Weyl group.
That's right. For the genus 1, you don't get that. You don't need that. That's not needed for that case. You just get the regular string. There's no Wilson line there.
Well, there is a discrete Wilson line, and you have it.
You can have some cases a discrete Wilson line, so it corresponds to a discrete analog of the spectral flow. That's what you're asking. In other words, the twisted sectors, there's Z2, for example, sometimes. Then you're talking about the discrete Wilson line. But that's when you want to get, that does not affect the leading Cardi formula either way. So it doesn't affect what I just told you. That you would have to do it if you have actually a string and you know how to go to the twisted sector of that string, which is that Z2 you're talking about, and calculating explicitly. But the central chart does not change.
But what I mean is if you take the F-theory associated to the genus 1 fibration, you have a discrete Z3 symmetry.
Yes. So you will go then to the twisted sector of Z3.
Exactly, but this is what the topological string on this Calabi-Yau calculates.
I know. But I'm just saying that for what you're saying is perfectly correct. But for the calculations what I'm doing, it does not affect the leading central charge because the central charge is the same whether you're in the untwisted sector, twisted sector. I didn't even go to that level of detail to even describe the discrepancy.
Okay, thank you.
Thank you for the nice talk. It's even surprising in 2D CFT that you can use the Cardi formula when n is of order C. So usually it's only works asymptotically. And in 2D CFT, it's known that you can extend the regime if you assume some sparseness condition on the spectrum. That was established by Hartmann, Stoiker, and Keller. So can you comment on whether you expect some maybe even stronger version of the sparseness to hold, and you can hope that some version of the Cardi formula holds in some extended regime?
I wouldn't know why it should work a priori. I mean, for example, here we have n of order root C even, not C. So no, I mean, to me, I don't have any insights into the question you're asking. It's an interesting question, but I don't have any insights to add.
Okay, thanks.
So as the underlying thing looks like, to have the kind of anisotropy between fiber and base. So I think the Calabi-Yau which one should look for this case is minimal H11 equal to 2. Because if you start with quintic anyway, I mean, even after making this transition, and then you are squeezing to a single modulus, right? So that means that this this fiber and base will have equal volume. I mean, this is the outcome, I think, what you are getting. So at least one should go beyond this quintic to test these things. I mean, I'm sorry to insist, but because the underlying requirement is that you need some kind of hierarchy or, anisotropy between fiber and base to have it in the end. So something like K3 fiber Calabi-Yau, say, in, this 1, 1, 2, 2, 6 or 1, 1, 2, 2, 4. So
I think that generically I don't expect to have a hierarchy between the elliptic fibration and the base class as long as the H11 is finite. Okay. In other words, you can imagine a situation where you have an infinite sequence of Calabi-Yau, which we don't have, in which case you get a collection of them, and as you go through them, you find the relevant elliptic fiber gets smaller, and so the charge gets relatively big compared to the other ones. That's possible in principle. But for a 2 or 3 or 4, I don't think you'll get there.
Okay, thanks a lot. Thank you.
When you say elliptic genus, which one do you mean?
What do you mean, which one do I mean? The usual elliptic genus. You have superconformal theory. On the one side, you have supersymmetry. On the other one, you don't. You just compute it.
Okay, I guess like from topological perspective, you're pushing forward one in elliptic cohomology, and that has you're choosing some elliptic curve or family of curves.
No, so to be more precise, you have a superconformal theory on the worksheet, which has supersymmetry on one side, and you don't have supersymmetry on the other side. You take an index on the supersymmetric side, and you get the partition function, which depends only on the non-supersymmetric side. That's what we do.
Okay.
Well, yeah, on a torus, you can think about it, yeah. Partition function on a torus, yes. Well, there's a torus which you can interpret it in terms of a circle that the string is winding around and a time, if you want to say it in the target language.
If there are no more questions, let's thank the speaker again.
Thank you.
Yeah.
Any chance that we can leave extra boundary conditions that require any chance? Is there any chance? Which means that if you want to implement the gap condition, you have to do everything and carry around the regularities. What the problem with the clinic is that even with ordinary means, the water means now, FG is 90, so it's too good already. One can still count constraints, one can still count one can fix it.
I think it's a good challenge. If you find a good answer. Go for it. You find it.
Different. Politicians transition different. If I will come back and compare the answers.
No, clearly you should get the same answer, but the computation you do will change in each case.
Yes.
None of them we know how to do the computation, so I don't know what to say. The answer should I agree? It's like saying that basically a topological string, if you do geometric transition, you can, if you change a Keller class and you blow down something, the geometric invariance or topological string on one side exists on the other side. That's all I'm using. So you say, oh, I can go the different way, yeah, but it will agree because you're computing geometric invariance. It's just that thing.
Okay, thanks.
The what?
Model space metric of the Taylor model sector and the
Not that I can see directly, no. I don't think modular space metric. Here, especially in 5D, the modular space metric is very boring. It's just like Keller comma. 4D. On the complex structure or Keller structure? Well, I don't think it would help you too much. For example, quintic mirror, we know the quintic mirror very well, but it still doesn't help us answer the question.
Spegniamo. La risoluzione non vedi? Ah, è perfetto, no? Perché prova a ricevere. vai, non preoccuparti. Perfetto, due lavagne allora. Ok.
talk e dopo avere domande.
E dopo vi faccio, rimetto i denti e dopo via. Come avete
sì.
fatto così,
Sì,
solita
sì.
roba. Ok. Ma come si accende?
No, è acceso, è acceso.
Bu. Okay, let's start the afternoon session. We have Mark Gross that will tell us about intrinsic mirror symmetry. Please.
Okay, well, thank you very much. It's a pleasure to finally be at Strings Math after many years of turning down invitations to attend. So I'm just going to start with some quick history without writing much down here. I've written down a list of references. So the story I'm going to talk about really begins with the Strominger-Alzazzo conjecture in 1996, which gave an explanation for mirror symmetry in terms of T-duality. And in particular, it suggested that mirror symmetry could be explained by having dual torus vibrations. So on a Calabi-Yau X and its mirror X check should each have torus vibrations, so something like X to B and X check to possibly the same manifold B. These would be torus vibrations. Special Lagrangian was usually assumed. And then to go from X to X check, you dualize these torus fibers. So this was a very vague conjecture. It still hasn't been proved at all in the degree of strength that Stranger and Zaslow conjectured, but it's inspired a huge amount of work, and in particular sort of led to this particular chain of ideas. So one of the key things that was sort of very visible early on in this story was that when you dualize these torus bundles, somehow the complex structure on X check is supposed to be determined by some other information on X. And the usual phrase that was used is there should be some instant-on corrections to the complex structure. And that was very hard to make precise or to see exactly what that meant in the early days of SYZ. So the first real attempt to deal with that was a paper of Fukaya in 2001. It's not on the archive, Asymptotic Analysis and Morse Theory, where he started to develop a picture which inspired many of us to try to make rigorous. The picture was very non-rigorous, but suggested that somehow you could understand the corrections of the complex structure by looking at things that look like tropical trees on the base following certain rules. So in 2 dimensions, this was made precise by Konsevich and Sullivan in a 2004 paper. They threw out all of the analysis involved in Fukaya's paper by working in the non-Archimedean setting. And then 3 years later, so this Konsevich and Sullivan did this in 2 dimensions, and myself and Siebert wrote a paper which did things in all dimensions, sort of generalized the Konsevich and Sullivan procedure to all dimensions. So this, both of these two approaches are really kind of algorithmic. They just tell you, here's a procedure for producing kind of the corrected complex structure on the mirror in terms of some tropical data on B. It was not, however, enumerative. But then there was some further development of ideas that came out of understanding what was going on in these 2 papers more deeply. In work I did with Hacking and Keel in 2011, we gave a much more general mirror construction for surfaces, for log Calabi-Yau surfaces, which you've already seen a hint of in Arguz and Bousseau's talk. And then in 2019, working with Bernd Siebert, we produced what I call is a completely general mirror construction. So this will not look very much like SYZ, but there is sort of a series of ideas which tells us that this really, what I'm going to tell you, is really the correct thing to look at. And it has the advantage, once we sort of have, the ideas have evolved for long enough, that it's now simple enough to explain in a 1-hour lecture. So without giving sort of any more history, I just wanted to get on and explain to you the general mirror construction. Okay, so what is our setup? So we're going to start with the log Calabi-Yau case. And what is a log Calabi-Yau? So xd is a log Calabi-Yau if x is a projective non-singular variety and D is an anti-canonical divisor, which is simple normal crossings. So one way to think about this anti-canonical condition is simply that x minus D has a nowhere vanishing homomorphic form, which has at worst simple poles along, has exactly simple poles along the boundary D. So here's a couple of examples. First case, would you take any non-singular toric variety, and take D to be the toric boundary, so complement of big torus in X. So this is a standard example. And this is by far the simplest example. So usually anything you want to do, you first test in that case. Here's a second example, which is the simplest non-toric example you might look at. We're going to start with this case. Let's take X bar to be P1 cross P1, along with its toric boundary. So I'll draw that like this. Here's the toric boundary. It's P1 cross P1, and the toric boundary is a cycle of 4 P1s. And I'm going to take a point here and blow it up. And I'll draw the exceptional curve as dotted because I'm not going to include it in the boundary. So I'll take D to be the strict transform of D bar. So this will be my running example, and I'll get back. I'll actually calculate the mirror to this at the end. And just as a third example, for which the construction also is going to give something useful, we can take the pair P2 with a smooth cubic curve. That's also allowed in this setup. Okay, so what are we going to do with this data? So the goal is we will construct a ring which I write as QH0 XD. And you should think of this as a kind of relative quantum cohomology with the 0 indicating that there should be some higher degree pieces of quantum cohomology that we haven't yet constructed. So this should just be suggestive. And this is, which should be, the ring of regular functions on the mirror. So I'm going to make this more precise as we go on, but sort of morally, this is what we're aiming for. We're going to actually construct a ring with some good properties. Okay, so of course, mirror symmetry started not in this kind of case of log Calabi-Yau's, but started with Calabi-Yau's. So let me say a word about how we connect this to the Calabi-Yau case. So to construct a mirror to the Calabi-Yau manifolds, we're instead going to consider maximally impotent, or what usually in the physics literature is called large complex structural limits. So you will start not with a single Calabi-Yau, but to a family, say, over a disk, with some very singular central fiber. Think, for example, of degenerating the quintic threefold to a union of hyperplanes in P4. And we apply the construction to the pair X, so this is now a manifold of one higher dimension, and with the divisor X0. And it turns out in this case we get a graded ring. QH0 of X, X0, with, which should be the homogeneous coordinate ring of the mirror. Now you might object that this is not a projective variety. We can assume it's relatively projective. But in fact, construction doesn't really care, just cares about the projectivity of the fibers and not the projectivity of the entire space. So the construction still works without any modification, and we get this extra structure, namely we have a grading on the ring, and we can view that as the homogeneous coordinate ring of the mirror. So from this point of view, the log-Calabi-Yau case is really the more fundamental case, and the Calabi-Yau case is just a somewhat special case, which is usually much, much harder to analyze in examples. So it's really much nicer to work in the log-Calabi-Yau case where we have some simple examples like that. Okay, so this gives you at least a hint of where we're going. We're going to construct this ring. And for this, I need first to give some little bits of data, introduce some concepts. So first, I'm going to talk about the tropicalization of XD. This is now a slightly fancier word for just talking about the dual complex of XD. But I'm going to go through this in some detail. So let's write D as some sum of irreducible components. So D1 up to DS. So for example, here we have 4 irreducible components. So we have D1 through D4. And a little bit of notation. I'm going to write div dx. This is going to be the free abelian group generated by the irreducible components. And I also want to write the dual. The dual abelian group. So this is Hom div dx into Z. And also the real version of that is Hom div d of x into R. Okay, so that's just a vector space whose dimension is S, the number of components. And I'll write these things have a basis given by the dual to the obvious basis of div D. Okay, so it's just a vector space. Okay, so now let's let P be the collection of this following collection of cones. I take cones generated by some subset of this basis, so subset indexed by set I. I is a subset of the set 1 through S, the index set for the irreducible components, with the property that the intersection of the corresponding divisors, the intersection of the di's for I and I, should be non-empty. So we have a cone in P. P is a collection of cones inside this real vector space. And we have one cone whenever we have a non-trivial, non-empty intersection of some collection of the DIs. And then I'll take just the subset of the vector space is just the union of all these cones. Okay, so that's sitting inside the vector space div d of x dual. Okay, so let's look at this again for our simple examples. So in the case where xd is a toric pair, in other words, x is a toric variety and d is the toric boundary, as in my first example, P just looks abstractly like the fan for X. So P agrees as a polynomial cone complex. With the fan for Px. However, it might be sitting in a much higher dimensional space. So for example, if you do this for P2, this would be three-dimensional because you have three boundary divisors as a triangle. So this is an abstract union of, well, it's not abstract, but it's a union of three cones sitting inside R3. So you lose the lattice structure for the fan. And as our second example, if we look at the blow-up I drew here, D1, D2, D3, D4, again, this just looks like something like this. We have four two-dimensional cones corresponding to the successive intersections D1 intersect D2, D2 intersect D3, and so on. So let me write generators here, D1 star, D2 star, D3 star, 4 star. But bear in mind, this is sitting in a piecewise linear way inside R4. So there's no fan, it's not a fan. Okay, so that's the tropicalization. That's one gadget we need. Okay, so we need to make one other choice. Well, this isn't a choice, this is just a construction. We need a choice of what I'll say called Kähler-Magi space. Now, for this, what I'm going to do is I'm just going to take a cone, i.e., choose a cone, sigma, contained inside the closure of the Kähler cone of X. All right, so this is sitting inside H upper 2 of XR, and sigma should be a rational polyjoule. Sorry? The effect here. Yeah, so it has no effect except this looks exactly like the same thing you get if you did P1 cross P1. It's of course going to have an effect later on, and we're going to look at this example. But this is sort of purely combinatorial data, which doesn't capture more subtle aspects of the geometry. Okay, so I'm going to choose a cone. Now, normally in mirror symmetry, if you go back to the very early days of mirror symmetry, people will write down the Kähler-Magi space as a tube domain. So let me just write this down to make contact with the old language, you would write down something like H2 of xr, that's the B field, plus I times this choice of cone sigma, or maybe the Kähler cone itself. You divide out by H2 of x z. Now, this isn't, and then what you would like to end up with is you would like your mirror family to live over this. Now, this is an analytic gadget, and we have a hard time proving any kind of convergence for the construction. So instead, being algebraic geometers, we work kind of order by order. And to do this, let's let P be the dual cone of sigma intersect the integral homology, h lower 2. So this is, well, if I ignore issues of discrete torsion, this is just contained as a submonoid of h of xr. And we have a toric variety. Let's let A be the monoid ring C bracket P. So the toric variety corresponding to sigma, I'll write like that, TV of sigma, toric variety corresponding to sigma. So an affine toric variety is just the spec of this monoid ring. Okay, so this Kähler homology space you can think of as sitting inside as some analytic open set inside this toric variety. And then you can use that toric variety to provide a partial compactification. So you end up with a neighborhood of the zero-dimensional stratum inside this toric variety, an analytic neighborhood, something. If I drew a two-dimensional example, the tube domain would have a partial compactification that looks like this. And as I say, we don't have a construction that works analytically. Instead, we're going to work in a formal neighborhood, very small formal neighborhood of this point large volume limit point. And the way we do that is we choose an ideal. So we choose any ideal, any monomial ideal. I, such that, so I, this is a subring of ideal in this ring A, such that A mod I is finite dimensional, is a finite dimensional C vector space. And let's give this a name. Let's call this AI. And what I'm going to do, the ring I'm going to build is a ring or an algebra over we'll construct QH0I of XD as an AI algebra. Okay, so we can do this for any monomial ideal, and this allows us then to take the limit. We define, these will all be compatible with various I, so we define this QH0 XD as being the inverse limit over all choices of I of QH0I of XD. And this will be a I should say we're taking the inverse limit over all I, and this will be an A hat, which is the completion of the ring A at its maximal ideal, or put another way, it's the inverse limit over all such quotient rings. Sorry, didn't finish the sentence. Okay, so this tells you what we are aiming for. If you're non-algebraically inclined physicists, I wouldn't worry too much about what's happening here with these inverse limits. Point is really to think of this as we're going to do a construction order by order around doing a perturbative expansion order by order at this large volume limit. And of course, we can't, as is often the case of perturbative calculations, we can't actually prove convergence in a neighborhood. But from the point of view of algebraic geometry, that's actually enough. Okay, so what I want to do is tell you now how to construct, for any given ideal I, I'm going to construct this ring, this module. Okay, so at one level, this is extremely easy. So define QH0 I XD. I'm going to, I didn't define this. I need to give one more definition first. Define B of Z. So remember I had this set which has now been erased, but B was this union of cones, so this is typical B. And I'll define B of Z to be the set of integral points in B, namely the set of things which are actually just integral linear combinations of the di stars. So that's B of Z. Some collection of points in B. So this would look like, in each one of these cones, it looks like a set of integral points in those cones. So it's an infinite set, of course. And now, I simply define QH0I XD as direct sum over P in B of Z, all points in integral points in B, AI times a symbol, which I'm going to write theta P. Now, if this was a slide talk, I want to emphasize that I would have used the tech command var theta rather than theta, but I just can't write a var theta. The point being that these are analogs of theta functions on abelian varieties. Okay, so what is this? This is just, I mean, there's nothing interesting going on so far. This is just a free AI module. So the only structure of X that has come into this so far is just the combinatorics of how the boundary divisors intersect. Okay, so our goal is to put an AI algebra structure on this flat AI module, or free AI module. So this is perhaps analogous when you define ordinary quantum cohomology. You just start with a vector space, namely the cohomology of X, and then you have to define a product which involves counting curves. And so the story is the same here. So we need to define structure constants. In other words, we need to know what happens when we multiply two of these theta functions, theta p times theta q. Well, that's going to be some sum alpha r pq of theta r, with each of these structure constants, in fact, living in the ground ring AI. Okay, so that's what we need to do to define this. And what about alpha RPQ? Well, I could think of this AI, if you recall, is it's the quotient of this monoid ring by the ideal I. So I could just write this as a polynomial. This is some polynomial, sum over A and P elements of the monoid which are not in I of some other number, NRA PQ, times T to the A. So this is an element of AI. So again, I haven't done anything. I'm just saying, well, an element of AI is a polynomial involving or a linear combination of these monomials for A, T to A should imply an I. So the key thing is to try to define what these numbers are to get something interesting. Oh yeah, so T to the A, let me perhaps write this. Oh, I just erased it here. Let me just do it over here. So here, think of C bracket P as being direct sum of A and P, C times T to the A. So in other words, T to the A is just the monomial corresponding to A and P. Okay, so here comes the subtle part. These numbers, which in fact will be rational numbers, are defined using a new kind, a relatively new kind of Gurr-Witten type invariant, which we call punctured Gromov-Witten invariants. And these were developed jointly with Abramovich, Chen, myself, and Siebert. Roughly in the period between 2015 and 2021, there have been about 3 or 4 versions of the paper, so I don't remember when we really actually managed to do it. Okay, so this being a talk to a very broad audience, I'm not going to get into the details of how to define these things. That's usually in sort of hardcore mathematics talks. Once you get into the definition, that's where eyes start to glaze over. There's no reason to go into that. And so I'll give you an intuition as to what's going on. So very roughly, we proceed as follows. So the first thing to observe is that R in B of Z induces or determines a stratum XR. So this will be some closed subset of X. How does it do this? Well, I can write R is some linear combination of the DI stars. And I can define XR is just the intersection over all I, such that AI is non-zero, necessarily positive then, of DIs. Now, this is necessarily, by the definition of B, of the cones in B, this is necessarily non-empty. Because P consists of those cones corresponding to non-empty intersections of DIs. Okay, so we get a well-defined stratum of And so simple examples, if I take the stratum corresponding to the point di star, that is just di, because there's only one non-zero coefficient. That's the coefficient of di. Okay, so now let's pick a point, pick a general point. Z in this stratum XR. And well, okay. You can now define NA, NR, A, PQ to be the count of stable maps, F from a curve C with 3 marked points, x1, x2, x out, to X, satisfying the following properties. So first of all, C is genus 0. Secondly, F represents the class A. Remember that the monoid P was contained inside the second homology of X. So F represents the homology class. That's the degree of the map. Third thing I want is I want to constrain the output point to map to Z. All of those are pretty standard conditions in ordinary curve-within theory. It's the next set of conditions that require considerably more technology. So F has contact order with the divisor di at x1. Sorry, let me insert this here. Contact order di, well, maybe I should write it. P evaluated on di. So remember, these points, B lies in the dual to the space of divisors. So we can evaluate P on di, or equivalently, just read off the coefficient of di and P. So F is contact order given by this to di at xi, sorry, at x1. F has contact order Q di, and I'm going to explain what this contact order means in a second, at di at x2. And 6, F has contact order. Now, leave a little space here if you're taking notes. I'm going to fill something in a minute. Sorry, this should be with, or 2. At x out. Okay. So I need to tell you what this contact order means, and I have to do that in a fairly efficient way. So you can impose tangency conditions. When you have a divisor on X, you can try to do things like count curves that have a given order of tangency with the divisor. And how do you define order of tangency? Well, if you have some divisor, let's say normal crossings divisor like this, and you have curve, maybe it does something like this, and a marked point there. So here's D1, for example, and here's D2. Then you can compute the contact order of this curve at this point with D1. You take the local equation for D1, I'll say T1 equals 0, and the contact order with D1 at the marked point. So here we have the map. This is, okay. The red thing indicates the image of the map. The contact order at the marked point X with D1 is the order of vanishing of the pullback of this function, T1 composed with F, at X. Okay, so in this picture, if you pull back the function T1, because this curve is maybe simply tangent to D1, the order of 0 will be 2. And similarly, you can do the same thing with D2, pull back the local equation for D2, and it will vanish to order 1 because the curve is transverse to D2. So that's the notion of contact order. So we're imposing these extra conditions. We're not just counting arbitrary curves, but we're imposing these tangency conditions based on the inputs, the P and Q, and then R. Now, the punchline here is that, as I said, I was leaving something out, is that actually the correct thing to do here is to put a minus sign. At which point you should say, what does that mean? That means a negative contact order. I'm talking about the vanishing of a contact order being measured by vanishing of a pullback of a function. So that's really the key technical heart in all of this that takes a lot of work to define. But we have this work with Abramovich and et cetera, has a way of defining negative contact order. And this was the key technical innovation that allowed us to actually do this. So I think in the time I have, I'd rather sort of say a bit about the ramifications of this and do an example. Where are my time-wise? 7 minutes, okay. Yeah, I'd like to do an example. Yeah.
Wheel theory? Or
no, not that we know of. We would like that to be true, but we haven't seen anything like that.
Theory of Gromp-Witten theory of curves. There's a usual relation between Hurwitz theory when you impose some branching condition, which looks like the contact order at the.
Yeah, no, I know. At the moment, we don't see anything like that. It could be it will emerge eventually.
In that case, it's known what's the condition.
Yeah. Okay, so I'll try to give a little hint as to what this means by way of example. But let me state a theorem. So the theorem is that these structured constants define an associative commutative algebra structure with unit being theta 0. Okay, now at a certain level, this theorem is obvious. If you know the proof of WDVV for ordinary quantum cohomology, you know exactly what to do. And sadly, the technical difficulties of dealing with these punctured Gromp-Witten invariants actually makes it quite a long-winded proof. But anyway, that is the construction. So let me do an example, which I promised again, to go back to this example here. So it turns out that there are only a couple of products you need to look at to understand the equations from the mirror. So in this case, one of the products is theta d1 star times theta d3 star. So that means that we're going to be looking at curves which meet d1 ones and meet d3 ones transversely, and then have some output point somewhere else. And it's not too hard to figure out that the output point can't have contact order with anything. Having zero contact order with all the divisors means that the output point just maps into the bulk of the log Calabi-Yau. So in fact, there's an obvious curve here. So I can fix my point z. The stratum corresponding to 0 is all of x. Just fix my point z somewhere in here. And then I have a curve that looks like that. We have x1 here, x2 here, and x out mapping as promised to z. There's one such curve. Hopefully you all agree with that. And the class of that curve is the same as the class of d4, so I can write this, maybe I'll use d2 instead. Write that as t to the d2 times theta 0. If you want to think of theta 0 as being the identity element, I can even erase the theta 0. So that one's easy. The other one which is slightly more interesting is this product. So again, sort of completely in analogy, let me draw the two contributions here. I have, again, a curve which meets the D2 and D4 transversely. So this would be x1 and this would be x2 with an x out mapping to the point z. And again, there's one such curve, and that curve, for example, is of class t to the d3. But now we have one more possibility. Which is a contribution to a coefficient of theta d1 star. Now, what does that mean? It means we're looking for a curve that meets d2 transversely and d4 transversely, and also meets d1 to order -1. So it turns out that that means the curve has to be entirely contained inside d1. So we have this output point which we've fixed inside d1, and then x1 would map here, and x2 would map here. And the way to think of this contact order -1 here is that the intersection number of the curve, which is d1, with the divisor sitting in, which is also d1, is -1, because we've blown up this point. So somehow we have to account for all the intersection of this curve with the divisor. We have to account for all the intersection by putting in the contact orders. So in this case, we put contact order -1 here. These 2 points, even though they're still contained in the divisor, we have contact order 0 with that divisor. So the magic of puncture-Grove-Witten theory, and more specifically logarithmic geometry, can keep track of that. So we have one curve like that, and then this contributes a contribution of t to d1. So it turns out that these two equations are the equations of the mirror. So the mirror family given by equations, and just to simplify life here, let me write x's instead of theta di's. x1, x3 is equal to t to the d2, and x2, x4 is equal to t to the d3 plus t to the d1 x1. So here you can think of these as being coordinates on Kähler moduli space. So as you move around in Kähler moduli space, the mirror changes a bit, but it's something living in an affine force space for any given value of the Kähler moduli. So I will stop there because I think I'm out of time.
Okay, thanks, Mark. Okay, are there questions? Remarks? One moment.
Sorry. Yeah. I think the protocol is you should say it through the microphone.
Could you maybe give some examples to explain why theta functions are theta functions?
Yeah, so if you apply this construction to a maximum unipotent degeneration of abelian varieties, you'll get a mirror family, which is a family of abelian varieties. And remember that when we look at degeneration situation, we're taking a proj, so we have the homogeneous coordinate ring. So the theta functions will be sections of a line bundle on that mirror family of abelian varieties. And they are theta functions. They are the classical theta functions in the theory of abelian varieties.
Thanks for the nice talk. I'm just trying to compare your way of thinking to the way we do in physics, the mirror symmetry. So pieces are similar, some pieces are not familiar, so I'm just trying to connect. So the idea that what we call the local Calabi-Yau, or what you're calling log Calabi-Yau on the generalization, is what you need to figure out first, and the compact one is the red herring in some sense, similar to the way you were proceeding. Yeah. That's a similar thing. The other thing is that for us, it doesn't apply. It doesn't need to be Calabi-Yau at all. So I'm assuming that's the same for you.
Yeah, that's right. So I didn't want to overload the talk with too many hypotheses. So at the moment, this ring exists as long as Kx, the canonical class plus the divisor, is either ample or anti-ample, or sorry, is Neff or anti-Neff, which means either it's non-negative on all curves or non-positive on all curves. So for example, if you take P2 with any smooth divisor, it will apply. The problem is that if you don't have the hypothesis, this is really a piece of a yet-to-be-constructed ring, which is not graded. And therefore, if you just take the degree 0 part, you won't have a well-defined product.
So then the next thing is that in the physics, again, proof, the simplest step we need to do is to find the mirror of the complex plane.
That's right, yeah.
Do you have the analog for that for you?
Yeah, so for the complex plane, so if you start with any toric variety, with the toric boundary, you get the Horry-Vafa mirror.
So the analog of superpotential for you is the relations you're writing?
Yeah, so the superpotential, I was going to say that if I had more time, is just summation of the theta di stars.
Oh, okay. Okay, thank you.
So what's special about D2 and D4 that they get this term from -1 contact order and D1 and D3 don't?
Yeah, so it has to, there's an asymmetry with broken symmetries, I can say that since the physics conference, by blowing up something on D1 but not on D2.
Okay, right.
So the point is that this curve has self-intersection -1. So curves can fall into it and be stuck inside it. Now, if I didn't choose my point generally, so for example, over here, in this one, I could have chosen the point over here and then had that curve, which still counts 1. But the point is that you should get the same answer wherever z goes, and in this case, you can move it out. Here, you can't move the yellow curve out because it's stuck in there. So somehow it has to contribute differently.
Okay, so it's determined by where you blow up.
That's right, yeah.
Okay.
Other questions? Yeah.
I'm going to ask you the question I always ask you.
Okay.
Which is, why is it that in your setup, a large complex structure degeneration is mirrored to a large complex structure degeneration?
I don't remember what I told you the last time you asked that question. So I think that the real point, if we first of all think about the log Calabi-Yau case, where the large complex structural limit would really mean maximally degenerate boundary. The point is that if the boundary isn't maximally degenerate, the mirror should not be affine, but should be, projective over something of lower dimensions. So the ring of regular functions is too small. So you can do this. You get a ring for P2 relative to a smooth elliptic curve, for example. And that is the ring of regular functions on the mirror, the properified mirror to P2. But it's not very interesting because it's just a polynomial ring. So to actually detect enough of the mirror in this way, you need to have a large enough ring. I don't know. I mean, there are many ways of answering your question. I'm happy to give 5 answers, but probably not now.
So we thank Mark again. So, the next speaker, okay, the speaker is Vivek Shende. Hi. Okay, and is going to talk about some exercises on scale-valued curve counting.
Hi. So, unlike Mark, I accept my invitations to string math. And the last time I was here was in 2019, and I talked about the same subject back then. And so I today provide an update. But first, I have to remind what I said on the previous occasion. And so let me, I will tell you what is, the title was Exercises in Skein-Valued Curve Counting. So first I explain skein, then I explain curve counting, and then I do the exercises. So let me start with the skein. So I'm going to write some formulas, and then I will explain what they mean. Okay, so these are the skein relations. They come from the study of this kind of quantum invariance of 3 manifolds and knots. And the skein, if I have a 3 manifold oriented, then the skein of M is a certain module. And it's given by framed links in M. Modulo, maybe it's the free algebra, the free vector space with basis framed links in M over, let's say, Q, A, Z, something like that, divided by these relations. And what these relations mean is that if you see 3 knots or 2 knots, which look the same everywhere but locally like these pictures, then you impose this relation. Okay, so that's what it is. That's the skein. And let me tell you 2 facts about the skein. The first is that the skein of the 3-sphere, this is just the ground ring. Under the map takes the empty link to 1. And the fact that this is true is more or less the same as the existence of the Humphrey polynomial. Because once you know this fact, you take any link you want, you send it over there, you get something, that's Humphrey polynomial. Okay. Or another way to say it is that this statement means that any link that you have, you use these relations enough, eventually you get rid of the link entirely using this one, and then you're left with number, and that's Humphrey polynomial. Okay, so that's one fact I wanted to tell you about the skein, and the other fact is that the skein of a circle times a disk, this thing is a free with basis given by pairs of partitions. The best way to think about this is if you have the kind of S1 times D2, it's kind of solid donut. A thing you can do to it is you can add from the outside a curve which looks like this, okay? And this uniquely determines a basis by asking that it be diagonal with respect to this operator. So there's a basis which diagonalizes this operator, and that basis is just the basis of the Wilson. I mean, so I said there's some connection to this kind of physics, and if you know it, you know what the Wilson lines in Chern-Simons theory are, and the basis corresponds to the basis of Wilson lines in some representation. And this fact here is more or less due to Turayev. So this fact is due to the people who came up with Humphrey polynomial. Okay, so that's about the skein, and now I want to talk about curve. So just keep that. I want to talk about curve counting. So this begins somewhere different. It begins with a Calabi-Yau 3x, Calabi-Yau threefold, and I allow myself a boundary condition. This is Lagrangian. And I ask that it satisfy the analog of the, so, you know, for Calabi-Yau, you ask Chern class vanishes. For Lagrangian, you ask an analogous condition, which is called being Maslov 0. It's just the analog of being Calabi-Yau. Okay, so we study some such thing, and we consider maps from a Riemann surface with boundary to XL. To begin with, one wants to try and study holomorphic maps. And there are a few facts about this problem that are important to know. The first one is that the kind of expected dimension of the space of such maps, which you learn from some index calculation, is 0. So the expected dimension 0. This is some incarnation of why string theorists like Calabi-Yau 3. Okay. And then the next important point about this thing is that the moduli space of such maps is non-compact, but Gromov long ago explained how to compactify it. So it admits this kind of Gromov compactification. And so once you have something which is compact in dimension 0,
you may think, well, if it was honestly dimension 0, it would just be a bunch of points, and you can count them, and you would be in business to define some numbers. But this word expected means that the equation which cuts the holomorphic ones out of the space of all ones is not transverse, and you have to perturb to make it transverse. So you perturb to make this well-defined. Perturb holomorphic curve equation. To get zero-dimensional moduli space. So that you can count. And there is an enormous amount of mathematics involved in this perturbing, which I won't begin to try and cite here. But it's been the work of many people for a very long time. But once you have done this, once you've done such a perturbation and gotten a count, you may like to know that 2 different perturbations gave you the same answer. Okay, so you have your perturbation, maybe C1 and C2. You have one parameter family of these perturbations. And you have your moduli space MC1, MC2, and you have this kind of moduli space here, and this moduli space here. And then you can consider the moduli space of solutions as you vary the perturbation. And because you've perturbed to make things transverse, some smooth one manifold, which everything is good unless it happens something like this. If this kind of thing didn't happen, which does not happen in the closed Gromov-Witten theory, when there is no Lagrangian, then you would know that the count on one side, at least with signs, is equal to the count on the other side because the whole thing is a boundary of a one manifold, hence 0. And so you learn inequality. But it turns out that when you allow a Lagrangian boundary condition, then you will find some families which just stop. So I want to now discuss which families, how this problem occurs. Okay, so we're good. So there's basically 2 things which cause problem. The first one looks like this. So I'm drawing a curve which ends on the Lagrangian. And I'll draw the boundary of the curve in white and the interior of the curve in green. Okay, and I'm considering a one-parameter family as I vary the perturbation. And what can happen in a one-parameter family is that the distance that you travel along this, any particular path, but for example, this path, the distance you travel along this path along the curve can go to 0. And if that happens, you wind up with this, this kind of thing. Okay? And this kind of thing, and this is a problem, your moduli space has stopped, even though your space of parameters is continuing. So this is one family of geometries which can occur as you vary perturbation. That's one problem. And the other problem, similar. The other problem is you have some kind of curve. I promised I would draw the boundary in white and the inside in green. So this is the inside. You have some kind of curve, and now the boundary can shrink as well. So it can happen that the boundary shrinks to a point. And so then kind of moduli space stops here. Maybe I'll draw the Lagrangian kind of in orange, even though the parameter space maybe continues. Okay, so these 2 problems mean that when you try and count holomorphic curves with boundary in one-parameter families, then some kind of problem. And so there's been various solutions to this problem in genus 0. Kind of Fukaya's great body of work gives you one kind of solution.
And I now discuss different kind of solution in a higher genus. So what to do? Well, you look at this curve, and in this one, it is a singular embedding of a singular curve which appears at the boundary of moduli space. But the same picture, it has also a different meaning. It also means the immersion of a smooth curve. So this is just a cylinder now, which can happen in the interior of the moduli space. And this one, unlike this one, it's finished deforming, but this one, it deforms smoothly. And what happens with this one, it looks a bit like this. So I mean, we're in 3 dimensions, and the boundary is a curve. You know, there's one manifold inside of a 3 manifold. So you expect it to meet itself in codimension 1. Okay, so as you deform, it looks like this. So I have this cylinder. I'm kind of varying parameters. And at some moment, the boundaries of the cylinder meet, then they cross each other, and I wind up with that kind of somehow self-linked cylinder. Okay. And so if you look at this picture, and you look closely, and closely means at this region, then you will see that the 3 different boundaries of the curve are the 3 terms of this Skene relation. You have to really see it, you would have to take them all and add kind of you have to add to all of them this kind of thing like this, add that to all 3 of them, and unwind it and rearrange it, you'll see this equation. Except for the z. The z in this curve counting story, it will appear because this guy has Euler characteristic 1 less than this guy. And so if I count everyone by z to minus the Euler characteristic, then I get exactly the difference between this side and this side is the Skene relation. So in other words, this curve counting, I ran into a problem here, and the problem was that 4 is not equal to 5 or something. But if instead of trying to count as numbers, I count the curves by their boundary in the Skene, this kind of wall crossing is exactly canceled by the Skene relation. Okay, so that cures the first problem. A second problem, you can try to do a similar thing. Yeah, so you can try to do a similar thing, which is you look at this guy, and you say he too could mean something else. He could mean a torus, which by accident, so I mean right now he means a torus with 1 boundary puncture, where the boundary puncture has length 0. But he could also mean a torus which by accident at one point hit the Lagrangian. And if I take that point of view instead, again it deforms freely in a family. So there's this kind of singular moment where this guy hits here. But he could go up and he could go down. Somehow he can, yeah. And so again, this one has an intersection. Here the intersection is a circle. Here there is no intersection. This is 2-dimensional. This is 3-dimensional. Generically, they should not meet. They'll meet in codimension 1 in a family. So if I try and play the same game, this one, this might start to look a lot like this, and indeed the z will appear for this genus reason. But how do I get the A minus A inverse? From the point of view of counting these guys by how they intersect this, this thing, I would be instructed to count them both as 0, or as the empty knot. And so it wouldn't help me any. And the solution to this is you ask what changes in this family. And so I said this is 2-dimensional, 3-dimensional, and a 6-dimensional space. And when you have things whose dimensions add up to 1 less than the ambient dimension, they don't intersect, but they might have linking number. And so what you can expect to change in here is linking number. And so I introduce something to capture the linking number. And how do you capture linking number? You have to, the most down-to-earth way is you say one of these things is the boundary of something, and you intersect the other one with that something. Okay, so I introduce some 4-dimensional guy, the 4-dimensional thing. And actually, I introduced 2 of them. And the 2 of them, they're kind of oriented oppositely. And you can set it up so that the kind of intersection number changes by, well, 2, because I've put 2 of them. So if I record everyone not only by z to the Euler characteristic, which I continue to do, but also by A to the intersection number with this 4 chain. So intersection with 4 chain. Then this wall crossing is also, it would cause a problem. But if you impose this, if you count things by their boundary and you impose this gain relation, then it cancels this, this wall crossing as well. But I've cured one problem, but unfortunately introduced another. And the new problem, which is introduced, is that, so if I'm going to count things by their intersection with this 4 chain, I better also do that to this guy. Okay? And if I'm going to try and define a linking number of someone which ends on something with that thing, I mean, I'm going to run into trouble. And the kind of trouble I'm going to run into is that, is the following. So I have, okay, let's just put this one again. And I put now this 4 chain. Okay. And I could have an intersection of the 4 chain and this curve, maybe here. And in a 1-parameter family, this thing could go to the boundary and fall off. And that would mean my count is not well defined. Right? Like how I count, which power of A I counted with, not well defined. And so, okay, well, let's see what happens. I have the one where I have the one where it's at the boundary. And then I have the one where it's fallen off entirely. It's gone now. And so this may trouble you because I've instructed you to count this one by A and that one by nothing. And so that would break my invariance of counting. And so I have to now say one more word about this 4 chain, which is that I choose it to have the following geometry, which is that I pick at the beginning of time some vector field on the Lagrangian. So I'm going to call this 4 chain, it's called W. And I'll call this guy V. And I demand, when you count holomorphic curves, you need complex structure. And so I demand that this complex structure J applied to V is somehow spans this direction of W, contains W. Okay. And this has the following effect. It means, I can use now this vector field. So generically, a vector field will be nowhere tangent to this kind of circle. But in a one-parameter family, of course, you can acquire such a tangency. And since I impose this condition, well, having this vector field tangent to the, what does it mean, this vector field is tangent to this circle? It means that, well, since this guy is holomorphic, J times the vector field also tangent to it. In other words, there's an intersection of W with this person exactly at the boundary. Okay, so this, imposing this condition means that at this moment, the vector field is tangent. And therefore, if I use this vector field to give a framing to the knot, then this change in intersection number exactly compensates the change in framing. Okay? And that is the third Skene relation. So maybe a theorem. And this theorem is with Tobias Ekholm. And we have finally, after 5 years, finished putting the kind of all the foundations to prove this in general. And the theorem is that, I just say it informally, this works. If you count curves by z to minus Euler characteristic, a to the intersection with the forward chain, class of the boundary in the skein, well defined. This gives an invariant count valued in the skein. So let me mention that, of course, a paper of Edward Witten in 1992, in some sense, predicts this theorem, but I am confused about how precisely and what the precise relationship is. So let me formulate some questions about this. I wrote down what my questions were. Yeah, so the first question is that in Witten's paper, the comparison between Chern-Simons theory and the holomorphic curve counting, it happened, as far as I understood, at the level of the action and the path integral. Whereas this comparison is happening somewhere else. It's happening in the moduli space of holomorphic curves. So the first question is, what is the relation between those two things? Second thing I'm confused about is that in Witten's paper, Chern-Simons appeared by studying the degenerate curves and how they contributed, and also Witten got out the kind of the Chern-Simons invariant of the three manifold. Neither of those things are anywhere to be seen in this picture. In fact, something we do, I mean, it's kind of consistent with something we do in the foundations, which is what we have to prove is related to the fact that we can exclude degenerate contributions entirely. So there's a fourth degeneration that could happen where a degenerate contribution of higher genus breaks off at the boundary. And what we prove there is you can perturb things in such a way this never happens. So that may be somehow related. The next thing is that, what is this four chain? So as far as I understood, in Witten's account and then the accounts in the string theory literature afterwards, they must have you guys must have some other way than this of finding this framing and dealing with this kind of crossing. So it's a mystery to me, what exactly is this four chain? Another mystery, maybe related, is that this A, I mean here, in Witten's paper, there's some like brain here. And in particular, the amount of brains has some meaning. And there's like some SLN, Chern-Simons theory for definite n. And no n has appeared in this story. Okay, and this A, it appears kind of formally. So it's related mystery. And then the last mystery I want to mention about this, mystery to me, it may be well known to people in the audience, is this kind of reasoning. What is the analog of that? Like for example, if this reasoning is correct, it must descend from some reasoning in actual string theory. It is like in the topological world. And like, what is that reasoning? And I've seen things kind of vaguely reminiscent in this kind of papers about background independence and so on, but I don't know how to pin it down. Okay, so those are my, I always ask a lot of questions, and these are my questions during my talk. Questions for you. Okay, so that was the skein-valued curve counting, but I promised today examples in skein-valued curve counting. So now I will do the examples. So we don't need the skein relation anymore. So the first example is related to something which Aguirre and Vafa discovered long ago. So this is related to this example 1. And it's related to this work of Aguirre and Vafa from long ago about knot invariance in topological strings. So they predicted or proved, depending on what kind of person you are, that if you want to study the Homfleet polynomial of a knot and also its colored variants are given by counting curves on some Lagrangian in the resolved conifold. So now I give mathematical proof of this statement. So you begin in a T star S3. And in T star S3, so this is supposed to be T star S3. And you have zero section. There's some S3. And I pick some knot that I want to study. Some knot I want to study. Maybe my picture has too many dimensions. Let's draw one dimension less. T star S3. And I pick some knot that I want to study, K. And I consider the conormal to K. Okay. And this S3 and this K, they intersect in a circle, which has Euler characteristic 0. So the intersection number is 0. And you expect you can push one off the other. In fact, you can. And so now this is kind of some n star k kind of pushed off a little bit. So I'll call it n star epsilon k. And let me count holomorphic curves in this geometry. It turns out not to be very hard. There's one. And this one holomorphic curve, it's if you set things up right, it's exactly the path traced by this knot as I push one of these guys off the other one. So you can arrange for that to be true. Okay, so the curve count is one holomorphic curve. But remember, I count these curves in a new kind of way. I count this one holomorphic curve by its boundary in the skein module. So this one is 1 times its boundary here, which turns out to be the longitude. So the conormal to the knot, topologically it's a solid torus, and its boundary here is the longitude of that solid torus. This thing we're not going to mess with. And well, its boundary here is just K itself. Okay. And so now, well, that wasn't very interesting, but I'll do a move that in symplectic geometry is called stretching. And I'm very curious how this move, is another question for you guys, how is this move related to things in physics? I'll discuss in a second more precise version of this question. So I consider a small neighborhood of this 3 sphere, smaller than this epsilon. And so I have the co-sphere bundle around the 3-sphere. And I degenerate the metric there. And so this is a well-studied operation in symplectic geometry. And what happens when you do it is, I think people have in this conference before talked about this operation, but just an algebraic geometry version. This is the thing where you have this like expanded degeneration and so on. So this operation, after you do it, you have a kind of copy of the cotangent bundle of S3 downstairs, and inside there you have the 0 section, and then you have a copy of the kind of cosphere bundle of S3 times R, and in here you have this n epsilon, n conormal to k. And the theorem that people prove in symplectic geometry is some version of the statement that if you count holomorphic curves here, it's the same as counting some kind of configurations of holomorphic curves in here, where you can have curves that do this kind of thing. So just they can live in one side, they can live on the other side, they can go from one side to the other side. But the things you have to know about, this is what they could do in general. But the thing you have to know about this is that when they cross, wherever they cross, it has to be along something called a Rabe orbit. So kind of in this this boundary, it has a natural vector field on it called Rabe vector field, and it needs to be orbit of this vector field. And it needs to be, for dimension reasons, a Rabe orbit of index 0. Okay? So this would be in general if I was doing some other geometry. However, what happens here is that, okay, first of all, now I've drawn a bunch of people who are actually illegal. This guy is illegal because the 0 section of the cotangent bundle is exact, and no holomorphic curve can end on an exact Lagrangian. So this one doesn't happen. Okay, so none of that. And in fact, T star S3 has the property that it has no Rabe orbits of index 0. This is related to the fact that S3 is kind of round sphere, so somehow like the index of this Rabe orbit is the same as the index of the corresponding geodesic. So Rabe orbits for like metric is just same as geodesics more or less. An index of Rabe orbit same as index of geodesic, and the geodesics of the round sphere all come in families, so index minimum is something like 2. Anyway, there are no such things. And what that means is that after you do this stretching, all the curves that you count live here. They could have had genus also. Okay, so they live here. And so let us count them. So the count, the curve count here is a sum, again. And by the way, I'm only, I should have said this. I'm only going when I said there was one curve here, what I meant was there's one curve that, so to speak, goes one time around. I fixed a homology class in which I study the curve. And so I'm going to keep that homology class fixed throughout this discussion. So on this side, again, you have some sum. So this curve count is some sum, and the thing I said about keeping the homology class fixed, it's 1 n star k. Tensor, well, the curves don't end here. Okay, so tensor empty set. And so it's some sum over all curves. I count them by some a to something, z to something, then this thing. So, okay, well, this thing is always the same. So this thing is some curve count. So I have curve count times L times empty. And by this argument I just gave, this was a deformation invariance argument. So I have proven that these things are equal. And well, I have here 1 LK, and here I have some mystery number, L empty set. But I told you that that's the definition of the Homfleet polynomial. If I take K and I write it as something times empty, then this something must be Homfleet polynomial. So this is a proof of this Aguirre-Vafa statement. Okay, that was example one. And more precisely, it's a proof of the kind of lowest order term in this Aguirre-Vafa prediction. Okay, so the next example, so example 2. This is related to a paper of Aganagic and Vafa in 2000. And also related to some math papers by kind of a little bit later of Katz and Liu and Graeber and Zaslow. Again, the precise relation is not entirely clear. This concerned the following question. You take C3, and you take this kind of Harvey-Lawson Lagrangian. And that is the thing which, in some kind of toric diagram for C3, people draw like this. Okay, so this one. And you want to count holomorphic curves ending on this guy. So you want to count this kind of stuff. So let me do it. I'm going to do it again by some kind of stretching argument like before. But this time, I stretch in a bit different place. Instead of stretching to separate the Lagrangian, here this time there's only one Lagrangian. And instead of stretching to separate the Lagrangian from the other Lagrangian, I'll break the Lagrangian itself. So this time, I have kind of C3. And then I have some kind of Lagrangian L. And I'm just going to stretch around some sphere, okay? Some kind of sphere of Lloyd radius. And when I do that, I have now some C3 and some S5 times R. And in here, I have this Lagrangian. This has the topology of a 2 torus times R. And this, again, is the original Aganagic-Vafa guy. Okay, and this time, so it's not so helpful to try and study the curve count directly with this breaking, because of course what happens is they just all go here and you learn nothing. So I'm going to do something else. I'm going to study, when I have a Lagrangian in the game, you can have holomorphic curves which go off to infinity and asymptotic to something what's called a Rabe chord of Lagrangian. And so it so happens there's a Rabe chord here of index 1. And I will study the moduli space of curves which kind of go up to this Rabe chord, travel along the Lagrangian, go out here, moduli space of such curves. Holomorphic curves whose boundary, holomorphic curves with one puncture, with a boundary, with a puncture, whose puncture goes up here, it's a boundary puncture, and the boundary travels along the Lagrangian. And similar kind of index calculation tells you that this moduli space, so let's call this Rabe chord rho, and the moduli space M of rho. So index calculation tells you that the dimension of this moduli space is 1, and I can study its boundary. And in this business of Floer theory, always the way we learn things, we look at boundaries of moduli space. So that's what I do here. I study this boundary, and well, what is it? Well, there's two kinds of things which can happen. One thing which can happen is this kind of boundary breaking, which we discussed before. And that boundary breaking, as I've already explained, it's all canceled by counting in the skein. So if I do the skein-valued count of the boundary of this moduli space, the contributions from boundary breaking contribute 0. But there's another it turns out there's another boundary contribution, and that has to do with kind of when stuff runs off to infinity. Okay, that's another boundary of this moduli space. And what that boundary looks like, this is kind of well-established stuff in symplectic geometry literature. That boundary looks like, it's similar to the discussion from before. In principle, you have holomorphic curves which look like this. And like do whatever they want in here, and then whatever they want in here, whatever. Okay, and then maybe something like this. Except for index reasons, again, it had better break at a Rabe chord of index 0. And a miracle of this geometry is that there are no such Rabe chords. So the only thing, it turns out, which can happen is that you get curves down here and curves which are up here. Okay? And so what I learned is that the count of configurations like this is a boundary. In other words, its count is 0. But what does that 0 mean? Where is that 0 computed? That 0 is computed in the skein. So I'm going to call the count of curves up here A, and I'm going to call the count of curves down here phi. And A is an element in the skein of this T2 times R. And phi is an element in the skein of the solid torus. And there's an action of this skein on this skein by I stick the T2 on the outside of the solid torus. And what this 0 means is that under this action, A phi equals 0. Okay, and phi is the thing I wanted to count. So it tells you that if I want to count phi, I could instead compute A and then solve this equation. So let me compute A. So what is A? A is curves which go up to this kind of Rabe chord here. And it turns out that I haven't told you yet what is that Lagrangian. So let me tell you now. If I have this S5, I can take the map that takes to P2, and I can take the map from P2, the moment map. Okay? And this Lagrangian is this Legendrian at infinity is the one, the thing at infinity is the one that maps under this composition of maps to this point under the moment map. So it's a 2 torus in P2, it's a Clifford torus, and then it's some multiple cover of that up here. But anyway, I can use this moment map to count those upstairs curves, it turns out, and there's 3 of them. That's it. That's the count. And that count is, if I write them in the skein, that count is 1 plus longitude, it's unknot plus longitude plus meridian. And I can ask, can I solve the equation this phi equals 0, psi equals 0? And the answer is yes. And then, so you can solve. And it's not difficult to solve because, as I said, there's a basis which is diagonal under the action of the meridian. This thing acts by a scalar, and this one kind of is upper triangular in that basis. So for this reason, it's not difficult to solve, and the solution is this kind of Wilson line with the partition lambda, sum over all partitions, Wilson line partition lambda. There's some kind of, and then some kind of combinatorial factor. There's a product over boxes in the partition, q to the c lambda, q to the minus hook length. It's not important, this formula. I mean, it's important, but it's not, for this talk, it's not so important. And that formula, in some appropriate sense, agrees with these previous calculations. But I get it in a bit different way. I get it by deducing a priori some relation that the whole thing has to solve, and then solving the relation. I did not count any of those curves. So maybe I'll do one last example. Let me mention a fact which is relevant to the last example, which is that if I take this equation and I specialize it, so here I was using Humphreys skein. I can specialize to U1 skein. U1 skein of T2 is quantum torus. And this is the polynomial representation of the quantum torus. And what this equation becomes in the quantum torus is the equation which defines the quantum dilogarithm. So this is some kind of fancy version of quantum dilogarithm. And that's relevant to the last example. Okay. Example 3. And this example 3 is related to this kind of work of Gautam-Warnitsky and the work of Fan and Nitsky. And this is like in 2012, and this is like in 2019 or something. And let me just describe, since I'm maybe low on time, I'll just describe the relevant geometry. So consider the following geometry. I begin with a Riemann surface, sigma. And I consider the geometry which is sigma times, I look at a cotangent bundle of sigma times r. Okay, and so this is sigma times r. And I fix a branched cover of sigma, so some sigma tilde. And this branch cover has branch points, and I allow kind of two of these branch points to collide and then come apart in a different way, some sigma tilde prime. And so this example is with some people. This is with some discussion. I learned this example last week. And so this is from discussions with Park, Alongi, and Ekholm. And so I study this geometry. And so this is some kind of cover, okay, some cover. And I take a knot down. I take a curve in sigma downstairs, a curve in sigma. And I take the conormal to this curve, and then I move it very far away. This is kind of curve, see. And I count holomorphic curves going down from this conormal of this curve down to this cover. Okay, and then there's two facts. The fact one, this defines a map from the skein of sigma in the variable a to the n to the skein of sigma tilde. And the second fact, which may be more interesting, is that I could have done the same thing on this side. So I could have done it here, I could have done it here. So I have similar map skein of sigma a to the n to skein of sigma, sigma tilde prime. And the map, again, the map is I take the curve, I take the conormal, I move it far away, and I count curves going down. It's obvious that defines a map from curves to here. It's not obvious it defines a map from the factors of the skein. But now, observe the following thing. What I should have actually done is counted not just, I should have counted all curves in this geometry. And it turns out that in this geometry, when I have this thing of these points colliding and then kind of separating a different way, I learn the name of one holomorphic curve. So in this geometry, there's this holomorphic curve and one more. Okay? And this holomorphic curve is a disk, and its local geometry looks very much like this disk. And so its count is psi, this psi in this game. So the total multiple cover count of this curve is, again, psi, more or less by that calculation. So what I learn is that in the skein of sigma tilde times r, I learn that let's call this map F and this map f prime. Okay, so in the scaling of sigma tilde times r, I learn that if I have f of c times psi, this way, is the same as if I had moved this over here and counted on this side. Is psi times f prime of c. And this, as I mentioned to you before, this psi, its specialization, the U1 skein is Q logarithm. And that means that this is a skein-valued cluster transformation. So maybe I'll stop there.
Okay, let's thank Vivek. One question there.
Thanks. Beautiful work. The relation to skein relations and the topological string. The way I interpret what you're showing is within Chern-Simon's description a la topological A model, together with your argument, implies that you can get the skein relation which should satisfy Humphrey. In other words, the target space interpretation of Chern-Simon can also be derived using the worksheet description. So that's the physics interpretation of what you have done. But let me comment on some of the questions you asked. So you were talking about the skein relation A minus A inverse being Z times the circle there. And you said there's no N here. Actually, I want to say there is an N in your formula, but you probably didn't notice it perhaps. You take one Lagrangian and you do this operation, you get one factor. Suppose you have two of them, what happens in a sequence?
The number of them does not appear in this.
No, but suppose you do the same operation you did. Go from Riemann surface above and go 2 steps down. Pass through 2 Lagrangians. What happens to you?
I should say that maybe in this picture, indeed some N appears here in this picture.
That's right. So I'm trying to say that you have, in some sense, forgotten about the degeneracy of the multiplicity of Lagrangian, and that's where it is. And the way it appears in physics is that Lagrangian, so the target space description of it, the way we understand it, which is related to the transitions we had with Gopal-Kumar, the Largent duality, is that the Lagrangian is a source of a unit of flux of Kähler form. In other words, the fact that there's a 2-cycle linking with the Lagrangian, each Lagrangian jumps the Kähler form by G string times the string coupling constant in 1 unit for each Lagrangian. So if you have N of them, N units.
I have a question for you. Why is it that this correction, or this fact, has never appeared when people in symplectic geometry study Fukaya category and so on?
That's them. I'm talking about the physics side.
I see.
You're asking a physicist why mathematicians don't do something. That's not fair.
No. But the fair version of this question is, how is it possible that they came up with a consistent theory without introducing this correction?
Well, again, you should ask them. But the description for us is clear. And the other question you asked was the framing. How does it appear in physics? Actually, in the same paper that you're mentioning there with Mina, we discussed that. That had to do with so there are 2 ways you can see that in the physics. One is the UV divergences that you see in the physics. But the way we got it was the boundary condition on field space. There's an ambiguity. And how you chose that ambiguity, basically the choice of the Lagrange P and Q variables in the quantum mechanics in a circle-valued version gave you a choice, and your wave function will vary depending on that. The choice of boundary condition becomes the choice of the angle framing that you had.
Can you turn that explicitly into vector field and forechain?
You probably can, but we didn't have that language. The language for us was in the same description that we have in that paper. We talk about, you have an action which is like U dV, so U and V are conjugate variables, and depending on which one you fix, or which combination of U and V you fix, you're choosing a framing. So there's an ambiguity about how you describe your wave function.
Just, it's maybe an additional example. What you will get if X will be a compact Calabi-Yau threefold and L to be a Lagrangian torus, that's a fiber of a SYZ fibration. Do you get something there, or?
Oh, I would need to have such an example. Probably, we've discussed this before personally, but I would have to first of all have some example where I could find this forechain.
So you're saying in this example, it's not even clear how to get a 4-chain, maybe. Maybe the 4-chain does not exist. Or
Yeah, I mean, it's a homological condition about
I
whether
see.
it exists or not.
Okay.
First of all, thanks for the lovely talk. So your picture is definitely much more complete than physicists would have had in 1992, partly because that was before we understood that D-branes are actually physical objects in string theory, and Polchinski hadn't yet discovered that D-branes carry Ramond-Ramond charge. One bit that was clear, and Vafa kind of said this, is that the parameters that I think you called Q and A correspond to what we would have called N and the string coupling constant. But a number of things in your story are not completely clear to me even now. So first let's discuss the 4-chain that's supposed to end on the Lagrangian. So I hope that that's a version of Polchinski saying that D-branes carry Ramond-Ramond charge, discovered around 1995, which says that, as usually expressed by physicists, there's a 2-form, D of which is the Poincare dual of the Lagrangian. So your 4-chain is the Poincare dual of that 2-form. Or maybe I should say better, the 2-form could be Poincare dual of your Lagrangian. So I hope that's what your A, you called it A, right?
Yeah, that's A, yeah.
I hope that that's what A means in physics, but there's something about the picture I don't understand. Maybe one of the physicists here does. The D-brane would be a source of Ramond-Ramond 2-form field that would couple to a D string. But for the rest of the picture leading to Chern-Simons theory, we have fundamental strings, not D strings. So I don't have a coherent understanding right now. I don't know if any physicist here can tell me what's missing in what I'm saying.
In the topological strings, the role that the Ramond-Ramond flux plays is played by Kähler form. That's what I was saying, basically. So the Kähler form plays that same role. So that's the sources. So the Lagrangian is the singularity in the Kähler form. That's another way of saying it. It's a source. It sources the Kähler form. With that, you can derive, for example, the topological string Lagrangian duality we had with Gopal Kumar. You can derive the relation he's mentioning. It's just that statement. There's no Ramond-Ramond field because we're talking topological strings. So indeed, you can show that it's a source of a Kähler form in that sense. It jumps the Kähler form.
Let me try to answer Ed's question maybe about this 4-chain. So in 1992, you explained that in the A model Lagrangian, the multiple Lagrangians carry Chern-Simons theory. But for Chern-Simons to be well defined, non-perturbatively, the level should be an integer. But you yourself explained that the string coupling constant is like 2 pi I over k plus n. And in this story, it was a just formal parameter. It was not quantized. So then it means that we're dealing with some kind of analytic continuation of Chern-Simons. But as you explained again, so that is actually 4-dimensional theory. So it's n equals 4 supermules living on some 4 manifold whose boundary is this 3 manifold. So I think it's beginning of the story where there should be n equals twisted n equals 4 living on this 4-chain, and so it just that's my comment.
Can I have a comment on this 4-chain?
Comments?
So my interpretation of this 4-chain actually, I mean, I had this 4-chain on compact Calabi-Yau's related, and we call this the tadpole cancellation condition, right? You have to, first of all, it's a condition on the existence of the 4-chain, right? That this Lagrangian has to be homologically trivial. And that can be interpreted in terms of what Edward said in the space-time. To get the Ramond-Ramond interpretation, you need to go to the superstring in the, and then you have an interpretation of this local cancellation of this Ramond-Ramond charge on the 2-dimensional defect in the Oguri-Vafa setup. And I think in the topological string, it should also be a type of tadpole cancellation, which has to do with the decoupling of the B model from the A model. So we had an interpretation of this 4-chain in compact Calabi-Yau case. Yeah.
Other comments, questions?
I think in a lot of applications in symplectic geometry, people really want numbers for some of these counts. Is there a way to kind of recover some numerical counts for like a particular perturbation or something from the skein theoretic counts that works in practice?
Oh, if you have something in the skein, like what is the skein? Skein is the thing you can feed the Chern-Simons. So if we did the Chern-Simons, it'll give you a number.
Okay.
I just want to put the first name of this guy, which I have written in my, because he's a young guy. This is Sung Hyuk Park.
Okay, so we can thank Vivek again. And please wait for a moment. There should be an announcement right now. No, Francesco? Here. Who is?
Sorry, there's a short presentation by Daniel about the Physics LATAM project.
Can you hear? Okay, great. Thanks to the organizers for giving me the opportunity to talk about Physics Latam. I think it will be the easiest talk in this conference. So what is Physics Latam? It's part of the project of ICTP, Physics Without Frontier. It provides online advanced lectures, workshops, seminars, and online resources to students and researchers who are facing socioeconomic barriers and getting quality education. So overview. So what we want to do is offer to students courses and mini courses on theoretical physics and mathematics, seminars with world-leading researchers, and our target initially was intended to be Latin American students, but then it became very big, and then we also start to accept people from developing countries, mostly undergrad students. So this is some of the programs. Can you see? Okay, great. Okay, so until now, it has been 2 years, but there is already like 600 students who participate in this project. As I say, it's from Latin American and developing countries. We strive for gender balance in our activities. All activities are conducted online, so everyone can attend and be part of it. Mostly the seminars are in Spanish and also in English. And every course that we offer, there are assignments, seminars, guest speakers, and a final exam. So we give a certificate for every course with a final score. The people sometimes can get credits from it from local universities. So this is the program so far. We start with quantum field theory, and then we have been able to offer all these courses so far. We are here offering right now general relativity. So each of these courses is like a 1 semester course. So it's like around 20 or 25 lectures each course. So far the people involved is 7 lecturers, a PhD and postdocs, 15 teaching assistants, 3 project assistants, and also Yashi is here in the audience. So for example, this is some of the people who enrolled in the quantum gravity course in last year, and also some people who enrolled in the geometry and topology in physics course last year. This is a distribution of students enrolled by each country, but this is not really outdated. This is from the beginning of this year. So past courses, you can see the course and how many people enroll in each course. So we offer quantum field theory, quantum gravity, geometry and topology in physics, general relativity and cosmology, algebraic geometry, classical and quantum black holes, quantum field theory, theoretical particle physics. Also, a lot of students who attend our courses, they manage to get accepted into international programs. For example, here in ICTP, this year 6 Latin American students were accepted into the ICTP diploma, and 5 of these students were enrolled with us. This is our seminar series. We host seminars the whole year. Usually it's like 1 or 2 per week, and I think all of you have seen this poster around all ICTP. All our seminars are on YouTube, in our YouTube channel, so you can go and go back to them anytime that you want. As you can see here, this is from last year. I think now there is enough seminars to fill like 4 times this quantity, but you can see very familiar faces. For example, Nikita, who gave a talk with us, is here. Pranav also, Mauricio Romo, and other people. I hope I'm not forgetting anyone. Okay, and we also have mini courses with guest speakers. So we have Mark Gross giving a lecture in Gross-Seaver program. So if it was too fast for you, the lecture today in 1 hour, we have like 10 or 12 hours of the same program. And well, we have also, last week, we finished algebraic topology in physics with Pavel Putrov, but we have other many speakers. Maybe I show you some recent talks and upcoming lectures. So we have already Robin Myers and David Bernstein giving talks, but soon we will have Nakajima talking about Nakajima quiver varieties, and Norbert Luckenhaus talking about QKD and quantum cryptography. Also, we have mini courses. We have 16 hours, I think it will be, about scheme and stacks theory by Barbara Fantecchi, string field theory by Professor Ashok Sen, quantum Riemann rock by Alexander Giventhal, and mirror symmetry and SYZ by Eric Zaslow, and many others. Actually, there are so many, but I chose to, I picked to show you the one that you might be interested to attend. The full schedule is here on our website. We also invite students, PhD students and postdoc, to talk students how to apply for particular programs, like advices and recommendations to particular programs around the world. We also, this year at the beginning, we organized our first conference for women in theoretical physics and mathematics from Latin America, in which we invite very distinguished professors, women professors from Latin America, to encourage more women in academia, in particular in physics and mathematics. Our current courses, who hasn't finished, is condensed matter field theory, quantum information theory, infinite dimensional algebra, and gauge gravity duality. Each of them has homework, exams, and has a guest speaker for each of them. And this is the number of students who currently are enrolled. This course started 2 weeks ago. It's general relativity and cosmology. Atish, director of ICTP, will give a talk on this, and we will have some also mini course associated to this course. This is a picture of me on Monday giving some lectures. And our coming courses, we have a classical and quantum black holes. And in this one, we will have Miguel Montero giving a mini course in Swapland program and applications to black hole physics, commutative algebra towards algebraic geometry, quantum field theory, theoretical particle physics. And this one be starting from September. This is impossible without the incredible help of all our teams of volunteers. Nobody gets paid, but everyone is willing to help us to bring this to people from developing countries. So the message is the PhD students, postdoc, and professor, I highly encourage to participate and help us bring in advanced courses to students in developing countries. For example, there are countries who cannot even access to general relativity, something so basic as it is, but they don't have access. And following the same spirit as Abdul Salam. And this is a picture of 16 years ago, Abdul having the key of this building that we are right now. So thank you to the ICTP and Physics Without Frontier, Bobby, Kate, Natasha, and many others for the support of our project, and to the organizers of Extreme Math 2024, and I hope all of you can have some time and participate in this project. Thank you.
Just one final thing about the streaming of the talk. The link is on the program webpage, I mean the conference webpage, if you need it or like it. And it will be streamed at 5 o'clock here.
Va bene una. No, adesso devo andare a prendere la macchina. Che mi
vabbè, dai, finché
no.
cose...
Ok, diciamo che l'ultimo anno non mi è morta, ma insomma, vabbè, sono robe, no, mi è morta mia mamma a settembre. Vabbè, vengo fuori da un anno un po'.
poi quando si mettono tutte in fila è pesante, no? Uno perde un po' le energie.
Un po' scoglionato. Però, dai.
Beh, mo inizia l'estate, magari uno fa un po' di tempo anche.
Ero incastrato a organizzare un meeting al GGI di Ressaggio e mi sono dopo la chiusa perché devo allenarmi, capisci? Quindi le gare, ma...
Bene, sì, dai, tutto a posto. Era parecchio che non ci vedevamo, lo stavo dicendo poi Domenico. Mi sembra che avevo visto a Strings 2 anni fa a Vienna.
Sì,
no, però...
borsa, sì, è rivenuta a Parma prima del Covid.
Sì, era...
19 era, sì.
Che mi ha detto questa lì, sono contenta.
No, Carlo, sì, adesso ho dato lezioni insieme a Michelangelo, quindi...
dai, bene, anche Michelangelo.
Michelangelo ormai anche lui è il giro giusto, quindi...
Se lo Carlo forse anche...
No, Carlo, dai, non sono contento. È pazzesco perché Carlo è un UFO. È un po' un UFO, cioè... No, nel senso buono del termine, però a volte... È un po' sulle nuvole, il suo mondo, in questo senso qua.
Sì, però è buono, e sia una persona molto buona che bravissimo.
Senti, no, ti dicevo un po' come...
Sì, io ormai appunto lo conosco da... Poi adesso c'ho tutti questi ragazzi, io ho detto, mo che tu fai? Quanti figli? 3, 4?
3. Adesso fra l'altro prendiamo una sinistra proprio sul suo progetto.
Dai.
Moglie non ha la patente, sai. Tra l'altro, stranamente, proprio stamattina mi ha scritto Grignani, che era un sacco che non lo sentivo.
Io lo sai, è una vita che non lo
Stamattina mi ha scritto, infatti devo rispondere, solo che nel casino non è ancora
ci credo.
ma stavamo parlando di atletica.
Pensa
Questi
di
giorni
cose,
qua.
poi c'è il tipo che ha vinto ieri.
Eh sì, appunto. Dai, senti, tu, ma dove fanno vedere sto talk di Witten adesso dov'è? Com'è? Ah, lo fai qua?
Sì,
Ma lui
ecco,
parla alla Sissa su.
alla Sissa su, sì, però io non ci vado
No,
più,
no.
anche perché devo essere
Sì, la regia
la
occulta.
regia. E poi perché sinceramente non ce la faccio.
Oh, dai, vado a
Sì,
prendere, ci vediamo dopo, vengo
tanto,
qua.
sì, sì.
Ok? Ciao.
Ciao.
Among four of the most pressing open problems at the time. Solving this problem could be as simple as finding a single number. So mathematicians have used computers and checked numbers up to 10 to the power of 2,200. But so far they've come up empty-handed.
Why do you think this problem has captured the imaginations of so many mathematicians?
It's old. It's simple. It's beautiful.
What else could you want?
So the problem is this.